Langchain experimental graph transformers LLM format property key. Definition. Defines the format of the property key in the graph transformers output. This property key is a crucial element in the representation of information extracted from text. It provides structure to the knowledge graph by defining the relationship between entities. For example, in a sentence like John works at Google, the property key would be works at connecting the entities John and Google. Components. Component 1. A key-value pair represents a single fact in the knowledge graph. Each fact in the knowledge graph is represented by a key-value pair. The key represents the relationship between the entities, and the value provides information about that relationship. For example, a key-value pair might be City New York, where city is the property key indicating a city and New York is the value, which specifies the city in question. Component 2. The property key is the name of the relation between two entities. This property key defines the type of connection between two entities in the knowledge graph. It serves as a label that clarifies the nature of their relationship. For example, in the pair born in London, the property key born in establishes that the entity being referred to was born in the city of London. Architecture. Graph transformers use a graph neural network to learn relationships between entities in a knowledge graph. Graph transformers leverage the power of graph neural networks to understand the complex relationships between entities in a knowledge graph. By processing the interconnectedness of entities, they learn patterns and relationships that can be used for tasks like knowledge extraction and question answering. Role. Enables the extraction and representation of information as structured key-value pairs in the graph. Transformers output. This property plays a vital role in shaping the output of graph transformers. By defining a standardized format for property keys, it ensures that extracted information is organized and readily accessible. The clear structure of key-value pairs facilitates the integration of knowledge into a meaningful and useful graph. Advantages. Facilitates the creation of a knowledge graph. The consistent use of property keys allows for the systematic construction of a knowledge graph. By providing a standardized vocabulary for describing relationships between entities, property keys enable efficient knowledge aggregation and the formation of a well-defined and comprehensive knowledge graph. Enables easy access to relevant information. The structured format of key-value pairs makes it effortless to retrieve specific information from the knowledge graph. By using the property key as a search term, one can quickly locate related facts and entities, simplifying the process of knowledge discovery. Challenges. Determining the appropriate format for property keys to ensure consistency and efficiency. The challenge lies in finding the right balance between flexibility and standardization. Property keys need to be informative and concise, allowing for clear representation of relationships while maintaining efficiency in storage and retrieval. Handling complex relationships and multi-hop reasoning in the graph transformer output. The output of graph transformers often involves intricate relationships that require reasoning across multiple hops. This poses a challenge for effectively representing and managing complex relationships in a knowledge graph. The format of the property keys should be flexible enough to accommodate these multifaceted connections. Potential for infinite loops if the graph contains cycles. The recursive traversal approach can lead to infinite loops if the graph contains cycles. This is because the function may encounter a loop where it keeps visiting the same nodes without reaching the root. Challenge 2. May not handle directed acyclic graphs (DAGs) correctly. The current implementation might not be optimized to handle directed acyclic graphs (DAGs). This is because DAGs have a more complex structure with potentially multiple root nodes, requiring modifications to the function to handle such scenarios effectively. langchainexperimental. LLMBash base LLMBashChain. A detailed explanation of langchainexperimental LLMBash base LLMBashChain in YAML format. Langchainexperimental LLMBash base LLMBashChain is a chain that runs bash commands using an LLM. This chain leverages the power of large language models (LLMs) to execute shell commands, effectively bridging the gap between natural language and system interactions. For instance, a user could provide a natural language query like "What is the current directory?" An LLMBashChain would translate this into a bash command pwd and execute it, returning the output to the user. Component 1. LLMBashChain uses an LLM and a bash runner. LLMBashChain operates by integrating two crucial components, an LLM and a bash runner. The LLM is responsible for understanding the user's intent and generating a corresponding bash command. The bash runner, on the other hand, takes this generated command and executes it within the system. Component 2. LLMBashChain utilizes a prompt template that combines the user input with the LLM's output to facilitate the interaction between the user and the LLM. LLMBashChain employs a prompt template. This template structures the user input and the LLM's output, ensuring clear communication between the components. The user's input is combined with the LLM's generated bash command within the prompt template, guiding the LLM to produce an accurate and executable command. The architecture is based on LangChain's chain structure. LLMBashChain adheres to the LangChain chain structure, a modular framework designed for building complex chains of components. This architecture enables seamless integration and communication between different components, allowing for flexibility and extensibility. LLMBashChain serves as a bridge between LLMs and bash commands, enabling the execution of commands based on LLM outputs. LLMBashChain acts as a bridge between LLMs and bash commands, allowing for seamless execution of shell commands using natural language instructions. For instance, a user could request list all files in the current directory and LLMBashChain would translate this request into ls command and execute it, returning the list of files in the current directory. LLMBashChain offers flexibility and enables the execution of bash commands by an LLM. LLMBashChain provides flexibility by allowing users to execute bash commands using natural language instructions, eliminating the need to write complex shell scripts. This flexibility empowers users to interact with the system in a more intuitive and natural way. It simplifies the process of interacting with bash commands through an LLM. LLMBashChain simplifies the interaction with bash commands by abstracting away the complexity of shell scripting. Users can interact with the system using simple natural language phrases. An LLMBashChain will handle the translation into executable commands. LLMBashChain relies on the accuracy of the LLM's outputs for the execution of bash commands. One of the main challenges of LLMBashChain is its reliance on the accuracy of the LLM's outputs. If the LLM generates incorrect or incomplete bash commands, it can lead to unexpected results or errors. It raises security concerns as it potentially allows LLMs to execute commands on the system. LLMBashChain also raises security concerns as it potentially allows LLMs to execute commands on the system. As LLMs are trained on massive datasets, there is always a possibility of the LLM generating malicious commands. Implementing proper safeguards and security protocols becomes crucial in mitigating these risks. LangchainExperimental, Graph Transformers.LLM.Map to Base Relationship. Detailed definition of the variable. Detailed definition of the variable goes here. Components. Component 1. The map to base relationship function utilizes the LangChain library, specifically the Graph Transformers class, to interact with graph-based language models. This function acts as a bridge between unstructured text and structured knowledge represented in a graph. Component 2. It takes a base relationship as input, which represents a relationship in the knowledge graph, and a text as a string. The function then leverages the LLM to identify the most relevant relationship between the provided text and the knowledge graph's base relationship. For instance, given a text, the capital of France is Paris and a base relationship is located in. The function might identify the most relevant relationship as is located in between France and Paris based on the text. Description of the architecture supporting the variable. Description of the architecture supporting the variable. The architecture leverages a graph-based language model, such as a transformer-based model, to understand the relationships between entities and concepts within a knowledge graph. This model processes the input text and the base relationship, then uses its understanding of the graph structure to find the most appropriate relationship between entities based on the provided text. Explanation of the variable S role in the system. Explanation of the variable's role in the system. This function plays a crucial role in bridging the gap between unstructured text and structured knowledge by mapping text to relevant relationships within a knowledge graph. It enables the integration of text-based information into a graph-based system, enriching the knowledge representation and enhancing its utility for various downstream tasks. Advantages of the variable. Provides a mechanism to link text-based information to structured knowledge within a graph-based system. This capability allows for the integration of diverse data sources, expanding the scope of the knowledge graph and enriching its understanding of the world. For example, this function could be used to automatically update a knowledge graph with new information from news articles, social media posts, or scientific publications. Enhances the ability to understand and interpret complex relationships between entities and concepts. By leveraging the power of language models, this function helps to uncover hidden connections and insights from the data. This can be particularly valuable in domains where relationships are intricate, such as scientific research, financial analysis, or social networks. Challenges of the variable. Ensuring the accuracy and completeness of the knowledge graph is crucial for effective mapping. The quality of the knowledge graph directly impacts the effectiveness of the relationship mapping process. Incomplete or inaccurate information can lead to incorrect inferences and undermine the usefulness of the system. This requires ongoing efforts to maintain and update the graph with relevant and reliable information. Handling ambiguity in text and complex relationships in the knowledge graph presents challenges for the LLM. Natural language can be ambiguous, and relationships within a knowledge graph can be intricate. The LLM must be able to handle these complexities and provide accurate and consistent mapping. This requires sophisticated language modeling capabilities and careful consideration of the specific domain and knowledge representation. LangchainExperimental, Graph Transformers.LLM. Create simple model. Definition of the function. This function simplifies the process of constructing a graph transformer model by leveraging the Hugging Face Transformers library. It involves setting up an appropriate model and tokenizer based on the provided model name, loading the model, and initializing the large language model instance. Components of the function. Component 1. Hugging Face Transformers. Provides pre-trained models and tokenizers for a wide range of tasks, enabling rapid model deployment. For example, a user could utilize a pre-trained model for sentiment analysis to analyze customer feedback data. Component 2. LangchainExperimental Graph Transformers (LLM). This module utilizes the underlying functionality of Hugging Face Transformers to enable natural language processing tasks within the LangChain ecosystem. It allows users to access and utilize pre-trained models and tokenizers for various natural language processing tasks, streamlining the development process. Architecture of the function. The function utilizes a chain of operations built upon Hugging Face Transformers to construct the Graph Transformer large language model instance. It involves selecting a suitable model and tokenizer, loading the model, and initializing the LLM. This process ensures that the model can handle language input and generate meaningful outputs. For instance, the function could be used to create a model that translates text from English to Spanish. Role of the function. This function simplifies the process of creating a graph transformer model for use within LangChain. Applications. It provides a convenient abstraction over the Hugging Face Transformers library, streamlining the model setup and configuration. It facilitates the integration of pre-trained models into LangChain projects, making it easier for developers to utilize these models for natural language processing tasks. Advantages of the function. Advantage 1. Simplified model creation. The function streamlines the model setup process, requiring minimal user input for configuration. This simplifies the process of creating and deploying a graph transformer model, allowing users to focus on their specific NLP task without needing to manage complex model configurations. Advantage 2. Pre-trained models. The function leverages Hugging Face Transformers' vast collection of pre-trained models, providing a wide range of readily available language models. This eliminates the need for users to train their own models from scratch, saving time and resources. Challenges of the function. Challenge 1. Model selection. Choosing the appropriate model for a specific task can be complex and require domain knowledge. Understanding the strengths and weaknesses of different models is crucial for achieving optimal results, and may require expertise in natural language processing. Challenge 2. Resource requirements. Large language models can be computationally expensive to load and run, requiring sufficient resources. This means that users need to have access to sufficient processing power and memory to utilize these models effectively. LangchainExperimental.LLM Symbolic Math Base LLM Symbolic Math Chain. A description of the LLM Symbolic Math Chain. A chain designed to handle mathematical expressions within large language model LLM. This chain aims to provide a bridge between human-readable mathematical expressions and the machine interpretable formats required for symbolic computation. Component 1. LLM Symbolic Math Chain. A chain that combines an LLM and a symbolic math interpreter to evaluate mathematical expressions. This chain acts as a bridge between human-readable mathematical expressions and the machine interpretable formats required for symbolic computation. It receives an expression as input, uses the LLM to translate it into a form suitable for symbolic math operations, and then applies the symbolic math interpreter to evaluate the expression. Component 2. Symbolic math interpreter interprets symbolic math expressions and applies relevant operations. This component is responsible for understanding and executing mathematical operations on symbolic expressions. It leverages the power of symbolic computation to perform calculations involving variables, functions, and complex mathematical constructs. Component 3. LLM provides language understanding capabilities to translate the input expression into a format that symbolic math interpreter can understand. This component is crucial for bridging the gap between human language and the formal language of mathematics. It uses its natural language processing (NLP) abilities to interpret and convert mathematical expressions into a form suitable for symbolic computation. The architecture combines an LLM and symbolic math interpreter. It receives an expression as input, uses the LLM to translate it into a form suitable for symbolic math operations, and then applies the symbolic math interpreter to evaluate the expression. This chain follows a two-step process. First, the LLM translates the input expression into a format that the symbolic math interpreter can understand. Then, the symbolic math interpreter performs the necessary symbolic math operations and returns the result. To handle mathematical expressions involving symbolic variables, functions, and operations using an LLM, this chain is designed to address the challenge of using LLMs for symbolic math operations. It aims to bridge the gap between human-readable mathematical expressions and the machine-interpretable formats required for symbolic computation, enabling LLMs to handle complex mathematical operations effectively. Advantage 1. Flexibility in handling diverse mathematical expressions. This chain provides a flexible approach to handling a wide variety of mathematical expressions. It can handle expressions involving variables, functions, and various mathematical operations, making it suitable for various mathematical tasks. Advantage 2. Leveraging the language understanding capabilities of LLMs to process complex mathematical inputs. This chain leverages the power of LLMs to understand and process complex mathematical inputs. By integrating LLMs into the workflow, it allows for the interpretation and manipulation of mathematical expressions that might be difficult for traditional symbolic math tools to handle. Challenge 1. The accuracy of the LLM in translating mathematical expressions into a format that symbolic math interpreter can understand. One of the main challenges is ensuring the accuracy of the LLM in translating mathematical expressions. The LLM's ability to correctly interpret and represent mathematical expressions is crucial for the chain's overall performance. Any errors in translation can lead to incorrect results. Challenge 2. The limitations of the symbolic math interpreter in handling certain mathematical operations, such as those involving advanced calculus or complex numbers. The symbolic math interpreter might not be equipped to handle all types of mathematical operations, especially complex or advanced ones. Its limitations can pose challenges in processing specific types of mathematical expressions. For example, it may struggle with operations involving advanced calculus, complex numbers, or special functions. This limitation can restrict the chain's ability to handle complex mathematical problems. LangchainExperimental, Graph Transformers. LLM. Map to base relationship. Definition. A detailed definition of the map to base relationship method. Components. Component 1. A graph transformer is a component that takes a base graph, a data structure that represents knowledge about relationships between entities as a directed graph, and applies a transformation to it. The transformation could be adding new nodes or edges, removing existing ones, or modifying the properties of nodes or edges. Component 2. A base graph is a directed graph that stores knowledge about the relationships between different entities. In a directed graph, nodes represent entities and edges represent relationships between them. These relationships can be of different types, such as is a, has a, or located in. Architecture. The architecture of the map to base relationship method is designed to convert relationships represented as key-value pairs within a dictionary into a base graph. A directed graph data structure that stores knowledge about relationships between entities. Role. The map to base relationship method plays a crucial role in creating a graph representation of knowledge stored in a dictionary of relationships. This method is essential for utilizing graph algorithms for knowledge discovery in reasoning tasks. For example, consider a dictionary that represents family relationships: Father John, Mother Mary, Son David, Daughter Sarah. The map to base relationship method would convert this dictionary into a base graph where each person is a node, and the edges represent the relationships between them. Advantages. The map to base relationship method allows for efficient storage and retrieval of relationships. This is because graphs can be stored and accessed in a way that allows for fast lookup of relationships between entities. The map to base relationship method enables the use of graph algorithms for knowledge discovery and reasoning. Graph algorithms can be used to find patterns and relationships in data that are not easily discoverable using traditional methods. For example, graph algorithms can be used to identify the shortest path between two entities, find the most connected entity, or discover clusters of related entities. Challenges. The map to base relationship method assumes that the relationships are in a specific format. If the relationships are not in the expected format, then the method may not be able to create a valid graph. For example, the method may require that each relationship be represented as a key-value pair where the key is the relationship type and the value is a list of entities involved in the relationship. If the relationships are represented in a different format, the method may need to be modified to handle the new format. The map to base relationship method may not be able to handle complex relationships. Complex relationships may involve multiple entities or multiple relationship types. The method may need to be extended to handle such complex relationships. For example, the method may need to be able to handle relationships that are not binary, e.g., relationships that involve more than two entities, or relationships that are not directional, e.g., relationships that are symmetric. Langchain experimental, LLMS anthropic functions. Anthropic functions. A comprehensive explanation of the class Langchain experimental, LLMS anthropic functions, anthropic functions and its key features. A class that represents a Langchain LLM based on Anthropic's application programming interface. This class provides a convenient way to access and utilize the capabilities of Anthropic's powerful language models within Langchain workflows. Langchain is a framework that simplifies working with large language models by providing tools for connecting models to various data sources and applications. Component 1. Langchain LLM refers to a language model implemented within the Langchain framework. It signifies a model capable of processing and generating text, translating languages, writing different kinds of creative content, and answering your questions in an informative way. Langchain LLMs are designed for integration with various components of the Langchain ecosystem, making it easy to build complex applications that leverage the power of large language models. Component 2. Anthropic Application Programming Interface, or Anthropic API, is a set of tools and protocols that allow developers to interact with Anthropic's language models programmatically. This API enables developers to send requests to Anthropic's servers, which then execute the requested language model tasks and return the results. Anthropic API provides a flexible and efficient way to utilize Anthropic's models for a wide range of applications, from natural language processing tasks to creative writing and more. This class integrates with Anthropic's application programming interface through LangChain, facilitating interactions between LangChain workflows and Anthropic models. This integration leverages LangChain's ability to connect language models to various data sources and applications, allowing users to easily utilize Anthropic's models within complex workflows. The class acts as a bridge between the powerful capabilities of Anthropic's language models and the flexibility of LangChain's framework, enabling seamless interaction and data flow. Enables seamless interaction with Anthropic models within LangChain workflows, allowing users to easily integrate the capabilities of Anthropic's language models into their applications. By providing a convenient interface for accessing and utilizing Anthropic's models, this class eliminates the need for complex integrations and manual configuration, simplifying the process of incorporating powerful AI capabilities into LangChain workflows. This class empowers developers to build sophisticated applications that leverage the strengths of both LangChain and Anthropic, leading to more efficient and effective solutions. Leverages powerful Anthropic models, renowned for their capabilities in language understanding and generation. Anthropic models are trained on massive amounts of text data, allowing them to generate creative content, translate languages, write different kinds of creative text formats, and answer your questions in an informative way, even if they are open-ended, challenging, or strange. Simplified integration with LangChain, making it easy to utilize Anthropic's models within LangChain workflows. This class provides a streamlined interface for interacting with Anthropic's API, reducing the need for complex code and configuration. Developers can seamlessly incorporate Anthropic's models into their existing LangChain applications, enhancing their functionality with advanced language processing capabilities. Requires Anthropic Application Programming Interface Key, which is a unique identifier that grants access to Anthropic's API. This key is essential for authentication and authorization, ensuring that only authorized users can access and utilize Anthropic's language models. Obtaining an API key typically requires registration and account creation with Anthropic, followed by a process to request and obtain the key. Limited control over model selection, as the class currently provides access to a specific set of Anthropic models. While this provides a straightforward approach, it might limit the flexibility of choosing models based on specific requirements or application needs. Users might need to explore alternative methods or request specific model access through Anthropic if they require a particular model not currently included. LangchainExperimental, LLMS Anthropic functions, Anthropic functions. A detailed description of Anthropic functions. A LangChain tool for integrating Anthropic's Claude with LangChain. A LangChain tool that allows you to access Anthropic's Claude large language model functionalities through LangChain's standardized interface. It enables you to call various Claude functions directly from your LangChain chains and applications. For example, you could use Anthropic functions to create a chain that generates creative text formats, translates languages, or answers questions using Claude. Component 1. LangChain is an open-source framework for building and deploying language model applications. It provides a modular and standardized way to connect different components of a language model pipeline, such as data sources, language models, and tools, making it easier to create and deploy complex language model applications. LangChain enables developers to build applications like chatbots, question answering systems, and document summarizers, leveraging various language models including Claude. Component 2. Anthropic's Claude is a powerful and safe large language model developed by Anthropic. Claude is known for its advanced capabilities in language understanding, text generation, and code generation. It excels at tasks like creative writing, summarizing factual topics, and answering complex questions in a comprehensive and informative way. It leverages Anthropic's application programming interface for communication, enabling users to seamlessly interact with Claude through LangChain. This means that users can access Claude's capabilities without needing to directly interact with the API themselves, simplifying the integration process. This tool acts as a bridge, connecting LangChain's ecosystem with Claude's capabilities for building sophisticated large language model-powered applications. It allows developers to take advantage of Claude's capabilities within the familiar LangChain framework, enabling them to easily integrate Claude into their existing LangChain chains and applications. Simplified integration allows using Claude within LangChain without needing to write direct application programming interface calls. With Anthropic functions, developers can use Claude within LangChain without needing to write complex API integration code, streamlining the integration process and focusing on building their applications. Streamlined development enables using Claude functions through familiar LangChain conventions. Anthropic functions allows developers to utilize Claude functions through the familiar LangChain interface, making the development process more efficient and intuitive. Application programming interface dependency relies on Anthropic's application programming interface for communication and functionality. It means that Anthropic functions' capabilities are tied to the availability and functionality of Anthropic's API. Feature parity might not fully mirror all Claude features offered by the native application programming interface, while Anthropic functions strives to provide access to a wide range of Claude features. It may not offer complete parity with the features available through the native Claude API. LangchainExperimental LLMs Anthropic functions. Anthropic functions definition. Anthropic functions is a class in LangChain that leverages Anthropic's Claude application programming interface for generating responses with the ability to call external functions. It allows users to define custom functions within their prompts and have Claude execute them during response generation. For instance, imagine a scenario where you want to generate a summary of a document but also include the document's author's name. You could define a function within your prompt that retrieves the author's name from a specified source and then have Claude incorporate it into the summary. Components. Component 1. LangChain, a framework for building applications powered by large language models. LangChain serves as a powerful tool for assembling, connecting, and orchestrating various components, including LLMs, to create intelligent applications. It simplifies the process of integrating LLMs into workflows, enabling developers to focus on building innovative solutions rather than managing intricate integrations. Component 2. Anthropic, an AI safety and research company that created Claude. Anthropic is dedicated to building safe and beneficial artificial intelligence systems. Claude, their flagship large language model, embodies this commitment by focusing on responsible AI development. Component 3. Claude, a large language model developed by Anthropic. Claude is a cutting-edge language model known for its ability to engage in natural and informative conversations. It can comprehend and respond to a wide range of prompts, making it suitable for various tasks like text generation, translation, and question answering. Architecture. This class extends LangChain's LLM base class, allowing for seamless integration with other LangChain components. It utilizes Anthropic's application programming interface to send prompts and receive responses, with the ability to handle function calls based on defined function specifications within the prompt. This architecture enables Anthropic functions to seamlessly integrate with existing LangChain workflows, enhancing the capabilities of LLM-powered applications by allowing for the execution of custom functions within the context of responses. Role. Anthropic functions enables the execution of custom functions within the context of Claude's responses, extending the functionality of the large language model and allowing for more interactive and dynamic applications. Imagine building a chatbot that needs to access external information, like a weather forecast, to answer user queries. Anthropic functions allows you to define a function that retrieves the weather data and incorporate it into the chatbot's response. Advantages. Integration with Claude for powerful language capabilities. Claude, with its advanced language processing abilities, provides a robust foundation for Anthropic functions, enabling users to harness its capabilities for tasks like text generation, translation, and summarization. Ability to call external functions within prompts. This key feature empowers users to extend the capabilities of Claude by incorporating custom functions into their prompts. For example, imagine a scenario where you want to generate a poem about a specific city. You could define a function that retrieves information about the city, such as its landmarks and history, and have Claude incorporate it into the poem. Simplified integration with LangChain's ecosystem. Anthropic functions seamlessly integrates with LangChain's existing ecosystem, offering a convenient way to leverage its extensive library of tools and components. This simplifies the process of building applications powered by LLMs, allowing developers to focus on innovation rather than complex integrations. Challenges. Dependencies on Anthropic's application programming interface and potentially associated costs. Using Anthropic functions necessitates relying on Anthropic's application programming interface, which may incur associated costs depending on usage patterns. Function execution limitations based on Claude's capabilities. The capabilities of Claude, while extensive, may limit the complexity of functions that can be executed. Potential for complex function definitions and integration. Defining and integrating functions within prompts can be challenging, requiring careful consideration of function parameters, return values, and potential side effects. LangchainExperimental, LLM Format Enforcer Decoder, LM Format Enforcer. A YAML representation of the LangChain component named LM Format Enforcer and its various aspects. LangChain component that enforces consistent output format from language models. It takes a language model and wraps it with a decorator that enforces the desired output format. This ensures that the output from the language model is always in a predefined format, making it easier to process and use in downstream applications. For example, it could ensure that all outputs are formatted as JSON, allowing for consistent parsing and extraction of information. Component 1. A language model is an artificial intelligence system that can generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. An example of a language model is ChatGPT. Component 2. Format enforcer ensures that data is represented in a specific format, allowing for consistent processing and interpretation. For example, it can ensure that all outputs from a language model are formatted as JSON, which can then be easily parsed and processed by other applications. LM Format Enforcer wraps the language model with a decorator that enforces the desired output format. This means that the LM Format Enforcer component acts as a layer between the language model and the user, intercepting the output from the language model and reformatting it before it is passed on to the user. This allows the user to always receive output in the desired format, regardless of the internal format used by the language model. Ensures consistent output format from language models. This means that the output from the language model will always be in a predefined format, making it easier to process and use in downstream applications. For example, it could ensure that all outputs are formatted as JSON, allowing for consistent parsing and extraction of information. Consistent output format means that the output from the language model will always be in a predefined format, making it easier to process and use in downstream applications. For example, it could ensure that all outputs are formatted as JSON, allowing for consistent parsing and extraction of information. Improved downstream processing because consistent output format makes it easier to process and use the language model's output in downstream applications. For example, if the output is always formatted as JSON, it can be easily parsed and processed by other applications. This can lead to more efficient and reliable processing of the language model's output. Can be challenging to configure correctly. This means that it can be difficult to set up the LM Format Enforcer component to work correctly with the desired format. For example, if the desired format is JSON, it can be challenging to configure the LM Format Enforcer component to properly parse and format the language model's output as JSON. May slow down model execution. This means that adding the LM Format Enforcer component to the pipeline can increase the time it takes for the language model to generate output. This is because the LM Format Enforcer component needs to process the language model's output and reformat it before it is passed on to the user. This can be a trade-off between the benefits of consistent output formatting and the speed of model execution. LangchainExperimental, Graph Transformers, LLM, Format Property Key. Definition. Specifies the format of the property key within the graph data structure. This property is crucial for maintaining consistency in how properties are identified within the graph and ensures efficient data retrieval. For example, in a social network graph, the property key name would be used to store the names of users. By defining a standard format for property keys, we ensure that all users' names are stored in the same way, regardless of whether the data is being retrieved from a database or a file. This allows for efficient searching and retrieval of data. Components. Component 1. A key-value pair data structure, where each key represents a unique property of the node or edge in the graph. For instance, a key-value pair could be named John Doe, representing a user node with the property name set to John Doe. Component 2. A string value associated with a specific key, storing the value of the property. In the example above, John Doe is the string value associated with the key name. Architecture. The graph structure is represented as a collection of nodes and edges, where each node has a set of properties. The format property key parameter defines how these properties are stored within the graph structure. For instance, in a knowledge graph, Each node might represent a concept, and the edges connecting them could represent relationships between concepts. The format property key parameter would define the format of the properties associated with each concept node, such as its definition, synonyms, or related concepts. Role ensures consistent and efficient access and manipulation of node and edge properties within a graph data structure by defining a standardized format for keys. This allows for the development of reusable and maintainable applications that interact with a graph data structure, as they can rely on the consistent format of the property keys. Advantages: simplifies property retrieval and manipulation, making it easier to work with the graph data. With a standardized format, accessing the names of all users in a social network graph becomes a simple task, as the same key name can be used to retrieve the value from every user node. Enforces uniformity across the graph, leading to improved data consistency. For example, in a knowledge graph, if all properties related to concepts were stored in a consistent format, it would be much easier to ensure data accuracy and prevent errors. Challenges: choosing a suitable format requires careful consideration to balance readability, efficiency, and compatibility with external data sources. A format that is too complex might be difficult to understand and work with, while a format that is too simple might not be efficient enough. Ensuring the chosen format aligns with the specific requirements of the application programming interface using the graph data. For example, if the application programming interface requires a specific format for property keys, the chosen format must comply with those requirements to ensure smooth integration. LangchainExperimental, LLMS Anthropic Functions, Tag Parser. Noun: a class that parses anthropic function tags from a string. This class is essential for understanding and utilizing anthropic functions within the LangChain environment, facilitating seamless interaction between language models and these functions. Component 1. The tag parser class. The core component of this functionality acts as the interpreter for anthropic function tags embedded within strings. It meticulously analyzes the structure of these tags, extracting crucial information for effective function integration. Component 2. The parse method serves as the primary mechanism for processing anthropic function tags. Through this method, the tag parser class decodes the structure of these tags, extracting vital information such as the function name, the input type, the output type, and a concise description of the function's purpose. The tag parser class leverages regular expressions, a powerful tool for pattern recognition within strings, to identify and extract anthropic function tags. The parse method then uses these identified tags to extract essential information, including the function name, its input and output types, and a descriptive summary of the function's purpose. This detailed information enables LangChain to effectively integrate and utilize these functions. The tag parser class serves as a bridge between the language models within LangChain and the diverse set of anthropic functions. By accurately parsing and interpreting the tags associated with these functions, the tag parser facilitates smooth communication and data exchange between the language models and the functions. This seamless interaction ensures that the language model can effectively leverage the capabilities of these functions, enhancing its ability to process and understand information. Advantage 1. The tag parser class significantly simplifies the process of understanding and integrating anthropic functions. By providing a structured mechanism for parsing and extracting essential information from function tags, it eliminates the need for manual interpretation, streamlining the integration process and enhancing efficiency. Advantage 2. The tag parser class efficiently extracts key information from function tags. This information, including the function name, input and output types, and description, is crucial for LangChain's seamless integration and utilization of these functions. It allows LangChain to effectively understand and interact with these functions, enabling them to perform specific tasks and enhance the overall functionality of the language model. Challenge 1. Handling complex tag structures presents a challenge for the tag parser class. As the complexity of tag structures increases, the parsing process may become more intricate, requiring robust algorithms to accurately interpret and extract information from these tags. Challenge 2. Ensuring compatibility with diverse function tag formats is an ongoing challenge. As the use of anthropic functions expands, ensuring that the tag parser can accurately interpret and utilize a wide range of tag formats is critical for maintaining seamless integration and functionality within the LangChain framework. For instance, the tag parser should be able to handle tags with different levels of nesting, variations in syntax, and diverse encoding schemes. Langchainexperimental, LLM decoder, ReLLM. A description of the ReLLM decoder and its components. Architecture, role, advantages, and challenges. A decoder implementation for retrieval augmented language models ReLLMs, which is an architecture that combines a retrieval component with a language model. A ReLLM decoder is a software component designed to process and interpret the output of a ReLLM. ReLLMs themselves are a powerful architecture that combines retrieval and language modeling capabilities. The decoder is responsible for taking the retrieved information and integrating it seamlessly into the generated text. Component 1. Retrieval component, e.g., a dense retriever retrieves relevant documents from a knowledge base. The retrieval component is the heart of ReLLM. It acts like a librarian, searching through a vast collection of documents to find the most relevant information for the query. A dense retriever, for example, uses techniques like embedding to represent both the query and the documents in a vector space. This allows for efficient retrieval based on semantic similarity. Component 2. Language model generates text based on the retrieved documents and the input prompt. The language model is the storyteller of the ReLLM. It takes the retrieved information and the user's query and crafts a coherent response. It uses its knowledge of language and grammar to generate text that is both informative and engaging. Large language models LLMs are commonly used for this purpose due to their ability to understand context and generate human-like text. The architecture uses a retrieval component to access and provide relevant information from a knowledge base in a language model to generate text based on the retrieved information. Imagine a question-answering system where the user asks a complex question. The retrieval component first goes through a database of articles and research papers to find relevant information. This information is then passed to the language model, which interprets the query and generates a comprehensive answer based on the retrieved knowledge. The role of the ReLLM decoder is to decode the output from a retrieval augmented language model. REM, which is a model that combines a retrieval component with a language model. The ReLLM decoder acts as a translator, taking the complex output from the REM and making it understandable for humans. It ensures that the retrieved information is presented in a coherent and meaningful way, while also preserving the original meaning and intent of the query. Advantage 1. Improved accuracy and coherence of the generated text by leveraging external knowledge. LLMs are known for their ability to produce more accurate and coherent responses by drawing on external knowledge sources. This allows them to provide answers that are grounded in facts and evidence, making them more trustworthy and reliable. Advantage 2. Ability to handle complex and nuanced prompts by incorporating external information. Complex queries, requiring specialized information, often pose a challenge for traditional language models. ReLLMs address this issue by incorporating external knowledge bases. They can retrieve information from various sources, like Wikipedia or scientific articles, and incorporate it into their responses. This allows them to answer questions with a higher degree of accuracy and sophistication. Challenge 1. Designing effective retrieval strategies to identify relevant documents. A key challenge in building ReLLMs is developing effective retrieval strategies. The model needs to be able to identify relevant documents from a vast pool of information. This involves creating efficient search algorithms that can accurately identify documents related to the user's query. Challenge 2. Ensuring that the retrieved information is integrated seamlessly into the generated text. Once the retrieval component identifies relevant information, the next challenge is to integrate it seamlessly into the generated text. The decoder needs to ensure that the retrieved information is presented in a coherent and logical manner, without disrupting the flow of the text. This involves ensuring that the retrieved information complements and enhances the overall message, rather than appearing as a disjointed or irrelevant addendum. Langchainexperimental, LLMS LLMBashChain, Chat Llama API. This YAML file provides a detailed description of the LangChain Llama API wrapper, outlining its purpose, components, architecture, role, advantages, and challenges. LangChain wrapper for the Llama API. This wrapper acts as an intermediary, simplifying the interaction between LangChain, a powerful framework for building language-based applications, and Llama API, an application programming interface API that provides access to large language models. It facilitates the seamless integration of Llama API into LangChain, enabling developers to leverage the advanced capabilities of these language models within their applications. Component 1. Llama API. This refers to the Llama Application Programming Interface API that provides access to the Llama Large Language Model. This API allows users to interact with the language model, providing input and receiving generated text outputs. Component 2. LangChain. LangChain is a powerful framework designed for building language-based applications. It provides a comprehensive set of tools and utilities that simplify the process of integrating large language models like Llama into applications. It offers features such as prompt engineering, chain building, and integration with various data sources. Wraps Llama API for using it with LangChain. The LangChain Llama API wrapper acts as a bridge between LangChain and Llama API, enabling the seamless integration of Llama API's capabilities within LangChain's framework. It simplifies the interaction by handling the communication between LangChain and Llama API, allowing developers to easily utilize the Llama language model within their LangChain-based projects. Enables LangChain to use Llama API for language generation tasks. The primary role of the LangChain Llama API wrapper is to empower LangChain to harness the capabilities of Llama API for various language generation tasks. It facilitates the use of Llama within LangChain, enabling developers to leverage its text generation, translation, summarization, and other language processing capabilities within their applications. Simplified access to Llama API within LangChain. The wrapper simplifies the interaction between LangChain and Llama API, providing an easier and more intuitive way to access and utilize Llama's features within LangChain's ecosystem. Developers can utilize Llama's functionalities with minimal effort, focusing on building their applications rather than dealing with complex API interactions. Streamlined integration with LangChain's functionality. The LangChain Llama API wrapper ensures a smooth and efficient integration of Llama API into the existing functionality of LangChain. It seamlessly integrates Llama's capabilities into LangChain's workflow, allowing developers to leverage both frameworks in a cohesive and unified manner. Dependencies on external Llama API service. The wrapper relies on an external Llama API service for its functionality. This means developers need to have access to a Llama API service and maintain a stable connection to utilize the wrapper's capabilities. If the Llama API service is unavailable or experiences downtime, the wrapper will be unable to operate. Potential limitations in API features. The wrapper's functionality is constrained by the features and limitations of the Llama API service. Developers may encounter situations where the Llama API lacks specific functionalities or limitations exist in its API, which could impact the wrapper's capabilities. LangchainExperimental, LLMS Anthropic Functions, Tag Parser. A class that parses tags from a string, using a predefined list of tags. This class is designed to be used with text processing tasks. For example, it can be used to categorize documents or to provide additional context for a given piece of text. This class is designed to parse tags from a string, using a predefined list of tags. This list of tags is specified when the class is instantiated. Component 1. A list of tags to be parsed. This list is used to define the possible tags that can be extracted from a string. For example, this list could include tags such as topic, category, and keywords. Component 2. A function to parse the tags from a string. This function takes a string as input and returns a list of tags that are found in the string. This function will search the string for the tags in the predefined list. The tag parser class uses a regular expression to match the tags in a string and then extracts them. This allows for efficient parsing of tags from a large number of strings. The tag parser class is used to extract tags from a string, which can then be used to categorize the string or to provide additional context. This can be useful for tasks such as document categorization or text summarization. The tag parser class is efficient and can be used to parse tags from a large number of strings. This can be useful for large-scale text processing tasks. The tag parser class is flexible and can be customized to parse tags from a variety of strings. This allows for the class to be used with different text formats and different tag sets. The tag parser class may not be able to handle all cases of tag parsing. This is because the class relies on a predefined list of tags, and it may not be able to identify all possible tags that could be present in a string. The tag parser class may not be able to parse tags that are not in the predefined list. This is because the class uses a regular expression to match the tags, and it will only match tags that are in the list. LangchainExperimental, LLMS Llama API, Chat Llama API. This YAML file describes the Chat Llama API class within the LangChain library. Chat Llama API is a powerful tool that facilitates the interaction with Llama API models, enabling users to leverage the capabilities of these advanced language models for various tasks. a class representing the Llama API chat model, facilitating the use of Llama API models within LangChain applications. The Chat Llama API class acts as a bridge between LangChain and the Llama API, allowing developers to access and interact with Llama API models for natural language processing. Tasks. Component 1. Llama API. A wrapper for the Llama API, a fast, scalable, open-source chatbot. Llama API provides an efficient and flexible infrastructure for deploying and interacting with large language models. It enables developers to quickly integrate advanced language capabilities into their applications, leveraging the power of these models for tasks such as text generation, translation, and summarization. Real-world applications include chatbots, content creation tools, and data analysis systems. Component 2. LangChain. A framework for building and deploying language models. LangChain empowers developers to create and integrate language models into various applications by providing a comprehensive set of tools and components. LangChain simplifies the process of building and deploying language-powered applications, facilitating efficient and scalable solutions. Examples include chatbot development, document summarization, and question answering systems. Chat Llama API leverages the Llama API and LangChain to enable seamless interaction with powerful language models. Chat Llama API acts as a central hub, seamlessly connecting LangChain with the Llama API's functionalities. This integration streamlines the process of accessing and interacting with Llama API models, providing a user-friendly interface for developers to leverage the advanced language capabilities of these models within their applications. Facilitates communication and integration with the Llama API for language-based tasks within LangChain applications. Chat Llama API acts as a bridge between LangChain and the Llama API, streamlining the process of interacting with Llama API models for tasks such as text generation, translation, and summarization. It simplifies the integration of Llama API models into LangChain applications, enabling developers to easily utilize the power of these language models within their workflows. Ease of use. Provides a streamlined interface for interacting with Llama API models. Chat Llama API simplifies the process of accessing and utilizing Llama API models, offering a user-friendly interface that minimizes the complexities involved in interacting with these models. This allows developers to quickly integrate and leverage the capabilities of Llama API models within their applications without needing extensive knowledge of the underlying infrastructure. Flexibility. Allows for customization of model parameters and application programming interface options. Chat Llama API provides developers with a high degree of flexibility in customizing their interaction with Llama API models. By allowing adjustments to model parameters and application programming interface options, developers can fine-tune the behavior and performance of the models to best suit their specific application needs. This flexibility enables the creation of highly tailored solutions, leveraging the full potential of Llama API models within a variety of contexts. API key management. Proper handling and security of application programming interface keys is crucial. The management and security of application programming interface keys are essential for ensuring the integrity and confidentiality of data when interacting with Llama API models. Strong security practices are crucial for protecting these keys from unauthorized access and misuse, preventing potential breaches and data leaks. Secure storage and handling of API keys are paramount to maintaining the security of applications and data. Rate limits. Adhering to application programming interface rate limits to avoid service interruptions To ensure smooth and reliable service, it is vital to adhere to the rate limits imposed by the Llama API. Exceeding these limits can lead to service interruptions and delays, hindering the performance of applications. Effective management of API requests within the designated limits is crucial for maintaining consistent and uninterrupted access to Llama API's functionalities. LangchainExperimental, LLMBashJS on-former decoder, import.js on-former. A detailed breakdown of the LangchainExperimental LLMJSON-former decoder import.js on-former. LangchainExperimental LLMJSON-former decoder import.js on-former, a function that imports the JSON-former decoder model. The JSON-former decoder is a specialized language model designed to decode JSON data by identifying and extracting key-value pairs. For example, it can take a JSON document like name John Doe, age 30, city New York, and extract the key-value pairs like name John Doe, age 30, and city New York. This makes the JSON data more accessible for human understanding and analysis. Component 1. LangchainExperimental LLMJSON-former decoder import.js on-former, a function that imports the JSON-former decoder model. The JSON-former decoder is a specialized language model designed to decode JSON data by identifying and extracting key-value pairs. For example, it can take a JSON document like name John Doe, age 30, city New York, and extract the key-value pairs like name John Doe, age 30, and city New York. This makes the JSON data more accessible for human understanding and analysis. Component 2. The JSON-former decoder itself is a sophisticated language model that has been trained on a massive dataset of JSON documents. It possesses the ability to understand the structure and syntax of JSON data, enabling it to identify and extract key-value pairs effectively. For instance, it can distinguish between different data types within a JSON document, such as strings, numbers, and booleans. This knowledge helps it accurately identify key-value pairs and decode JSON data with high precision. The architecture of the JSON-former decoder is based on a transformer network, a powerful neural network architecture commonly used for natural language processing tasks. The transformer network employs a mechanism called attention to focus on relevant parts of the input JSON data, allowing it to extract meaningful information. This attention mechanism allows the model to prioritize certain parts of the JSON data based on their importance in decoding the information. By focusing on the most relevant parts, the JSON-former decoder can efficiently extract key-value pairs and produce accurate results. The role of the JSON-former decoder is to decode JSON data into a more human-readable and structured format. It achieves this by identifying and extracting key-value pairs from the JSON input, making the data easier to understand and analyze. For example, if a JSON document contains information about a product, the JSON-former decoder can extract information like the product name, price, and description. This decoded information can then be used for tasks like creating reports, building dashboards, or training other machine learning models. Advantage 1. Efficient JSON decoding. The JSON-former decoder significantly simplifies the process of decoding JSON data, making it a more efficient and streamlined approach. This means that instead of manually parsing JSON data, which can be time-consuming and error-prone, you can rely on the JSON-former decoder to automatically extract the information you need. This efficiency can save developers and data analysts significant time and effort. allowing them to focus on other tasks. Advantage 2. Enhanced accuracy. The model's training on a vast dataset of JSON documents ensures high accuracy in identifying and extracting key-value pairs. This means that the JSON format decoder is less likely to misinterpret or misclassify the data, leading to more reliable and trustworthy results. Challenge 1. Handling complex JSON structures. The JSON format decoder might encounter challenges when dealing with intricate and nested JSON structures, potentially leading to inaccurate decoding. For instance, if the JSON data contains multiple nested objects, it might be difficult for the model to accurately identify and extract all the key-value pairs within those nested structures. This is because the model might struggle to understand the complex relationships between different elements within the JSON data. Challenge 2. Limited context awareness. The model might have limited context awareness, resulting in difficulties in correctly interpreting complex JSON data that requires understanding the relationship between different elements. For example, if the JSON data contains information about multiple products, the model might have trouble understanding the relationships between different products within a data. This can lead to inaccurate decoding or the extraction of irrelevant information. Langchain experimental, LLM format enforcer decoder, LM format enforcer. Description of Langchain experimental, LLM format enforcer decoder, LM format enforcer. A specialized wrapper class designed to ensure consistency and uniformity in the output formats of language models LLMs by enforcing a predefined structure. This class serves as a bridge between the user and the underlying LLM, ensuring that the output adheres to a predetermined format, regardless of the LLM's natural output style. This guarantees consistent data structures for downstream processing and analysis, simplifying the interaction with LLM responses. Component 1. The LM format enforcer class is the core of the solution. It encapsulates the logic for intercepting the LLM's raw output and applying the formatting rules defined by the decoder function. It acts as a middleware, ensuring that the final output adheres to the desired format. Component 2. The decoder function is the heart of the LM format enforcer. This function takes the LLM's raw output and transforms it into the predefined structured format. The decoder's complexity depends on the diversity of the LLM's potential output structures and the desired output format. It plays a crucial role in ensuring uniformity and interpretability of the LLM responses. The LM format enforcer wraps an existing LLM, acting as an intermediary between the user and the LLM. It intercepts the LLM's output and processes it through a dedicated decoder function, which ensures that the output conforms to the predefined format. This architecture enables users to interact with LLMs through a standardized interface, regardless of the inherent variability in LLM responses. Standardizing LLM output by imposing a strict format, simplifying downstream processing and analysis of LLM responses. By enforcing a uniform output format, the LM format enforcer simplifies integration with other tools and systems. The standardization reduces the need for custom parsing logic and enhances the reliability of LLM-driven applications, leading to more consistent and predictable results. Streamlined data processing. Consistent output format simplifies parsing and analysis of LLM responses. This ensures that LLM responses can be easily integrated into various downstream applications, without the need for extensive custom parsing logic. This facilitates efficient data processing and analysis, leveraging the structured output for tasks such as data extraction, knowledge base updates, and machine learning applications. Enhanced reliability ensures predictable and standardized LLM outputs, reducing potential inconsistencies or errors. By enforcing a specific format, the LM format enforcer eliminates the variability inherent in LLM responses, leading to more predictable and reliable results. This standardization enhances the robustness of applications relying on LLM output, reducing the likelihood of errors caused by unexpected response structures. Decoder complexity: implementing an effective decoder function to handle diverse LLM output formats and enforce the desired structure. The decoder function needs to be robust enough to handle the diverse range of output formats that LLMs can produce. It requires careful design and implementation to ensure accurate and efficient parsing of the LLMs. Raw output. Potential limitations: the predefined output format might restrict LLM's flexibility and ability to generate alternative responses. By enforcing a strict format, the LM format enforcer might limit the LLM's ability to express diverse or nuanced responses. This could potentially impact the creativity and flexibility of the LLM, as it may not be able to generate responses that fall outside the defined format. langchainexperimental. LLMBashChain bash process. langchainexperimental. LLMBashChain bash process. This class represents a bash process, which allows you to run bash commands using a large language model LLM as a code interpreter. This class takes an LLM as input and uses it to execute commands on a remote server. For example, a user could utilize this class to automate a process of retrieving data from a remote server by instructing the LLM to generate the necessary bash commands and then executing those commands on the server using this class. Component 1 represents a bash process, allowing you to run bash commands. This component enables the execution of bash commands within a managed environment, providing a controlled interface for interacting with the bash shell. Component 2 code interpreter to execute commands on a remote server. This component leverages the capabilities of an LLM to generate and execute bash commands on a remote server. For instance, a user can provide a natural language instruction to the LLM, such as download the latest file from the server, and the LLM will translate this into appropriate bash commands, which are then executed by this component on the remote server. This class is built on top of the LangChain framework, providing a way to utilize large language models LLMs for executing bash commands on a remote server. It leverages the LLM's capabilities for generating and executing commands within a secure and managed environment. For instance, the class provides a way to ensure that only authorized commands are executed on the server, mitigating potential security risks. This class acts as a bridge between large language models (LLMs) and bash environments, facilitating the execution of bash commands using the LLM as a code interpreter. This enables users to leverage the LLM's capabilities for scripting and automation tasks within a bash context. For example, a user could leverage this class to automate a complex series of bash commands required for data processing. By providing natural language instructions to the LLM, the LLM would then generate the required bash code, which would be executed on the remote server via this class. Simplifies bash command execution using large language models (LLMs). This allows users without extensive bash scripting experience to leverage LLMs to automate tasks. For example, instead of needing to write complex bash commands, A user can simply provide a natural language description of the desired task, and the LLM will automatically generate the corresponding bash script. Leverages LLM capabilities for advanced scripting and automation. This enables users to perform complex tasks within a bash environment, such as processing large datasets, interacting with APIs, or managing system configurations, using the LLM's ability to understand and generate code. For instance, a user could utilize this class to automate the process of retrieving data from a remote server by instructing the LLM to generate the necessary bash commands and then executing those commands on the server using this class. Security considerations when executing code from an LLM. This class requires careful security considerations to ensure that only authorized code is executed on the remote server. For example, the class might employ mechanisms to sanitize input from the LLM and restrict the execution of potentially malicious commands. Potential for unexpected behavior from the LLM's code generation. The LLM's code generation might not always be accurate or reliable, potentially leading to unexpected behavior or errors. For instance, the LLM might generate incorrect bash commands, which could result in unintended consequences. Langchainexperimental LLMS llama functions pass response. Definition. The pass response method in langchainexperimental LLMs functions is responsible for parsing the response received from llama application programming interface and transforming it into a format that can be used by LangChain. It handles different response formats and extracts the required information like generated text, function call, and metadata. Components. Component 1. Pass response method in langchainexperimental LLMs functions is responsible for parsing response received from llama application programming interface and transforming it into a format that can be used by LangChain. It handles different response formats and extracts the required information like generated text, function call, and metadata. Component 2. llama application programming interface is a service that provides access to powerful language models for various tasks, such as text generation, translation, and summarization. It offers a flexible API for interacting with these models, enabling developers to integrate them into their applications. Architecture. The pass response method is a part of the langchainexperimental LLMs functions module, which provides integration for llama in LangChain. It interacts with llama application programming interface and processes the response according to the specified format. Role. The pass response method plays a crucial role in facilitating seamless integration between llama and LangChain. It acts as a bridge between the two systems, transforming the response received from llama into a format understandable by LangChain. Advantages. Advantage 1. It provides a standardized way to handle responses from llama, ensuring consistency and ease of use for developers. By having a consistent format, developers can easily work with responses from llama, regardless of the specific model or API used. This eliminates the need for custom parsing logic for each response format, simplifying integration. Advantage 2. It enables LangChain to leverage llama's capabilities for tasks like text generation, translation, and summarization. LangChain can use the pass response method to extract the generated text, function call, and metadata from llama responses, allowing it to utilize llama's powerful language models for various NLP tasks. This opens up a wide range of possibilities for developers, enabling them to build sophisticated applications with LangChain. Challenges. Challenge 1. Handling different response formats from llama can be complex, requiring robust parsing logic to extract relevant information. llama may support various response formats depending on the model or API used. The parse-response method needs to handle these different formats effectively, ensuring that all necessary information is extracted correctly. This requires careful consideration of data structures and parsing logic, which can be challenging due to the potential for variations in the response format. Challenge 2. Ensuring compatibility between llama and LangChain requires careful consideration of data structures and API design. Both llama and LangChain have their own data structures and APIs, and ensuring compatibility between them is crucial for seamless integration. The parse-response method plays a key role in bridging this gap by converting the responses received from llama into a format that LangChain can understand. This requires careful consideration of both systems' data structures and APIs to ensure a smooth and efficient integration. LangChain experimental graph transformers LLM format property key. Definition. The format property key parameter in the LangChain experimental graph transformers LLM class is used to specify a function that will be applied to the keys of the input dictionary. The function will be invoked for each key value pair in the dictionary and can modify the key before it is passed to the underlying transformer model. This functionality is crucial for ensuring that the keys of the input dictionary are aligned with the specific format expected by the chosen transformer model. For example, if the transformer model requires keys to be in a specific case, or to have a particular prefix, the format property key function can be used to apply these transformations before passing the keys to the model. Components. Component 1. The format property key is a user-defined function that is provided as an argument to the LangChain experimental graph transformers LLM class. This function accepts a single argument, which is a key from the input dictionary. The function can then modify the key as needed and return the modified key. The LLM class will then use the modified key to access the corresponding value in the dictionary when interacting with the transformer model. For instance, the function might be designed to convert keys to lowercase, or to add a specific prefix to each key, depending on the requirements of the chosen transformer model. Component 2. The LLM class from the LangChain experimental graph transformers module leverages transformers, which are a powerful class of deep learning models designed for natural language processing tasks. Transformers work by processing sequences of words, typically represented as tokens, and capturing complex relationships between them. These models often have specific format requirements for the input data, such as expecting keys in a particular case or with specific prefixes. The format property key function plays a vital role in ensuring that the keys of the input dictionary are compatible with these format requirements. Architecture. The format property key function operates as a bridge between the input dictionary and the transformer model, allowing the user to define custom transformations for the dictionary keys. This transformation process ensures that the keys are correctly formatted for the transformer model, preventing potential compatibility issues and enabling seamless integration. For instance, a user might define a function that converts all keys to lowercase or adds a specific prefix to each key, depending on the specific requirements of the chosen transformer model. This function would be executed for each key in the dictionary before it is passed to the transformer model, ensuring that the input data adheres to the model's expectations. Role. The format property key parameter plays a crucial role in ensuring that the keys of the input dictionary are compatible with the format expected by the underlying transformer model. It acts as a bridge between the user-provided data and the model's specific requirements, facilitating seamless interaction and preventing potential errors due to incompatible input formats. This parameter allows users to customize the key transformations based on the chosen transformer model, ensuring that the data is presented in the most appropriate format for the model to process effectively. This flexibility is crucial for leveraging the power of transformers effectively, as they often have specific input format requirements. Advantages: flexibility in adapting keys to transformer requirements. The format property key function empowers users to customize the format of the dictionary keys before they are passed to the transformer model. This flexibility is essential for working with diverse transformer models, which often have specific requirements for the input data. For example, some models may require all keys to be lowercase, while others may require them to have specific prefixes. The format property key function allows users to tailor the key formatting to meet these requirements, ensuring seamless integration with the chosen model. This flexibility also makes the langchainexperimental graph transformers LLM class more adaptable to different transformer architectures, increasing its utility for a wide range of natural language processing tasks. Improved compatibility with diverse transformer architectures. The format property key function facilitates smoother integration with diverse transformer architectures by allowing users to customize the formatting of the input dictionary keys. This customization ensures that the data is presented to the model in the format it expects, maximizing compatibility and minimizing potential errors due to incompatible input formats. This approach enables the langchainexperimental graph transformers LLM class to work seamlessly with a wide range of transformer models, enhancing its applicability in various natural language processing scenarios. Challenges: requires careful design to ensure key transformations are accurate. The format property key function is a powerful tool for tailoring input data to the specific requirements of transformer models. However, the design of this function needs to be carefully considered to ensure that the transformations are accurate and do not introduce unintended changes to the data. Incorrect transformations can lead to unexpected behavior and errors during the processing of data by the transformer model. For example, a function designed to convert keys to lowercase might inadvertently change the meaning of some keys, leading to incorrect results. This underscores the importance of careful design and testing to ensure that the transformations are correct and that the resulting data remains accurate. Potential for complex logic if intricate key formatting is needed. The format property key function provides a flexible mechanism for adapting the format of the input dictionary keys to the requirements of transformer models. However, in scenarios where complex formatting is required, the logic of the function can become intricate, leading to increased code complexity and potential for errors. For instance, if the transformer model requires specific prefixes and suffixes for the keys, the logic for applying these transformations can become quite complex. This complexity can make it more difficult to maintain and debug the function, as well as increase the risk of introducing errors during implementation. In such cases, careful planning and modularization are crucial to ensure that the logic remains manageable and function operates correctly. langchainexperimental.palchain base PAL validation. A YAML representation of PAL validation. Its definition. Components. Architecture, role, advantages and challenges. PAL validation is a class that provides a mechanism to perform validation on a proposed plan. Generated by a PAL chain. A PAL chain is a framework for planning and automating complex tasks using large language models. The validation process ensures that the plan is coherent, feasible, and aligns with the user's objectives. Component 1. PAL chain, a framework that combines large language models and planning techniques to generate automated plans for complex tasks. Component 2. Validation function, a function or set of rules that examine the generated plan and assess its adherence to predefined criteria. For example, a validation function could check for resource availability, feasibility of steps, and potential conflicts in the plan. PAL validation is integrated with the PAL chain, acting as a post-processing step after plan generation. This means that the generated plan is first passed through PAL validation to ensure its validity and compliance with established constraints. This integration is designed to enhance the reliability and quality of the generated plans. PAL validation ensures that the generated plan adheres to specific criteria and meets the desired constraints. This involves assessing the plan against various validation criteria, such as feasibility, resource availability, safety, and compliance with established regulations. Improved plan quality. The validation process ensures that the generated plan is well structured, consistent, and adheres to the desired criteria. This leads to more efficient and effective plans, minimizing errors and maximizing success. For instance, a travel plan validated for feasibility might include realistic travel times, considering traffic and potential delays. Increased reliability by verifying the plan against established constraints. PAL validation enhances its reliability. The validation process can identify potential issues or inconsistencies that could lead to errors or unexpected outcomes. Defining appropriate validation criteria. Establishing effective criteria for validating a plan can be challenging, as it requires a comprehensive understanding of the specific task and the context in which it is executed. Defining criteria that are relevant, specific, and unambiguous is critical for ensuring the effectiveness of the validation process. Handling complex validation logic. The validation process might involve complex logic, especially when dealing with intricate plans or multifaceted constraints. Developing algorithms and functions that can handle such complexity while maintaining efficiency and accuracy can be challenging. For instance, a complex plan for managing the supply chain might involve intricate validation rules for inventory levels, transportation routes, and delivery schedules. Ensuring efficient validation execution. Validating plans can be computationally intensive, particularly for complex plans with numerous constraints. Optimizing the validation process to ensure efficient execution while maintaining accuracy is crucial for real-time plan generation and execution. LangChain experimental PAL chain summarized. NaN. A chain that uses a specific persona to generate responses, aiming to provide personalized and engaging interactions. For example, a chain could be designed to simulate a friendly travel agent, providing tailored advice based on user preferences. Component 1. A chain that takes user input and a defined persona as input, producing a formatted response that aligns with the specified persona. For example, if the persona is a travel agent, the response might be formatted as a travel itinerary or a list of recommended hotels. Component 2. A chain that takes user input and a defined persona as input, producing a formatted response that aligns with the specified persona. For example, if the persona is a teacher, The response might be formatted as a lecture or a series of learning exercises. This chain is composed of multiple subchains, including a retrieval chain and a generation chain. The retrieval chain gathers relevant information based on the user input and the persona, while the generation chain uses this information to produce a personalized response. The primary function of this chain is to provide personalized and engaging responses to user queries by incorporating a specific persona into the interaction. This allows for a more interactive and tailored experience for the user. This chain offers a more personalized and engaging experience compared to generic chatbots. By employing a persona, it can better adapt to user preferences and provide more relevant information. For example, a chatbot designed to act as a travel agent would provide more engaging and tailored recommendations compared to a general-purpose chatbot. This chain can be utilized to create more complex and sophisticated conversational agents. By combining multiple subchains, it can perform tasks like information retrieval, question answering, and creative writing, all while maintaining a consistent persona. Defining and maintaining the persona can be challenging, as it requires careful consideration of the desired personality traits and the specific context of the interaction. For example, ensuring that the persona remains consistent and engaging over time can be challenging. This chain can be slow and resource-intensive, especially when dealing with complex tasks or large amounts of data. This can limit the scalability and responsiveness of the chain in real-world scenarios. LangchainExperimental. Chain, base, PAL validation. A comprehensive overview. PAL validation is a powerful LangChain component designed to validate the responses generated by a language model LM based on a set of predefined rules. It's an integral part of the PAL chain framework, a structured approach to building reliable and trustworthy AI applications. Component 1. PAL validation class, the foundational class that encapsulates the validation logic and provides methods for defining and applying validation rules. Validation function, a reusable function or method that implements a specific validation rule. It takes a generated response from the language model as input and returns a Boolean indicating whether the response meets the validation criterion. Component 2. Evaluation metrics. These metrics are used to assess the quality of the language model's responses after validation. Commonly used metrics include accuracy, precision, recall, and F1 score. For example, in a chatbot application, accuracy might measure the percentage of responses that are factually correct. Precision might measure the proportion of responses that are relevant to the user's query. PAL validation operates within the PAL chain architecture, which promotes a modular and structured approach to developing language-based AI applications. It interacts with the LM component to receive generated responses and the evaluator component to measure the quality of these responses based on defined criteria. For instance, an LM component might be responsible for generating text responses, while an evaluator component would assess the quality of these responses based on predefined metrics or rules. PAL validation is a critical component in the PAL chain framework, ensuring the reliability and trustworthiness of AI applications built upon large language models. LLMs. It serves as a quality control mechanism, verifying the accuracy and consistency of the responses generated by the LLM. For example, in a medical diagnosis system, PAL validation would ensure that the LLM's responses adhere to established medical guidelines and standards. Increased confidence in LLM outputs. Validation provides a higher level of assurance in the outputs generated by the LLM. This confidence is crucial in applications where the LLM's responses have real-world impact. Improved accuracy and reliability of AI applications by filtering out invalid or inaccurate responses. PAL validation enhances the overall reliability and trustworthiness of AI applications. This is particularly critical in domains like healthcare, finance, and legal where accuracy is paramount. Reduced risk of unintended consequences by validating responses. PAL validation can mitigate the risks associated with unintended or unexpected consequences arising from the LLM's outputs. This is especially important when deploying AI applications in sensitive domains where ethical considerations are crucial. Enhanced user experience validation can lead to a smoother and more satisfactory user experience by ensuring that users receive accurate and consistent information. In a chatbot application, for instance, validation helps prevent the chatbot from providing incorrect or misleading information, thereby enhancing the overall user interaction. Defining appropriate validation rules can be challenging. Especially for complex tasks, the process of defining validation rules that comprehensively capture the intended behavior of the LLM can be complex, especially for tasks involving intricate logic or domain-specific knowledge. Maintaining a balance between rigorous validation and computational efficiency. Striking a balance between thorough validation and computational performance is essential. Overly complex validation rules can slow down the processing time, potentially hindering the overall efficiency of the AI application. Ensuring that the validation rules accurately capture the intended behavior of the LLM is crucial. To ensure that the validation rules accurately reflect the intended behavior of the LLM, mismatches between the validation rules and the LLM's behavior can lead to inaccurate assessments of the LLM's outputs. Handling edge cases and unexpected inputs. Validating the responses generated by the LLM against a predefined set of rules is critical to ensure the overall accuracy and reliability of the application. However, real-world scenarios often involve unexpected inputs or edge cases that might not be explicitly covered by the validation rules. Therefore, it's important to have mechanisms in place to handle these situations gracefully. Langchainexperimental, LLMSRLM decoder, ReLLM. A detailed description of the ReLLM language model. ReLLM is a decoder-only language model that aims to improve text generation performance by focusing solely on the decoding process. It leverages the concept of decoder-only architecture and incorporates various techniques to enhance its capabilities. Component 1. A decoder-only architecture. Eliminating the encoder and focusing solely on the decoding process. This architecture allows for faster inference speeds and reduced computational costs, as the model only needs to process the input sequence once. For instance, in a machine translation scenario, the decoder-only architecture would directly translate the input sentence into the target language, without needing to first encode the input into a hidden representation. Component 2. Various techniques, including attention mechanisms and positional encoding to capture long-range dependencies in sequence information. Attention mechanisms allow the model to focus on specific parts of the input sequence when generating the output, while positional encoding provides information about the order of words in the sequence, which is crucial for generating coherent text. For example, the model might use attention to focus on specific words in a sentence that are relevant to the current word being generated, or it might use positional encoding to ensure that the generated text follows a logical order. The architecture consists of a stack of decoder layers. each comprising multiple sublayers, such as multi-head attention, feed-forward networks, and layer normalization. The decoder layers process the input sequence step by step, generating one output token at a time. Each layer performs a series of operations on the input sequence, including attention, feed-forward networks, and layer normalization, which help to capture long-range dependencies and generate meaningful text. For example, the multi-head attention layer allows the model to attend to multiple parts of the input sequence simultaneously, while the feed-forward network layer applies nonlinear transformations to the input sequence, which helps to learn complex relationships between words. To generate coherent and meaningful text by decoding the input sequence and predicting subsequent tokens, REM takes an input sequence and generates a sequence of output tokens, one at a time, based on the information in the input sequence and the model's internal state. The goal is to generate text that is both grammatically correct and semantically meaningful, and that captures the intent of the input sequence. For instance, if the input sequence is a question, REM should generate a response that answers the question in a clear and concise manner. Advantage 1. Improved text generation quality due to optimized decoder and attention mechanisms. The optimized decoder architecture allows the model to better understand the relationships between words in input sequence, which leads to more coherent and fluent output. The attention mechanisms allow the model to focus on specific parts of the input sequence that are relevant to the current word being generated, which helps to ensure that the generated text is both relevant and meaningful. For example, in a text summarization task, the model might use attention to focus on the most important sentences in the input document when generating the summary. Advantage 2. Efficiency by removing the encoder. Allowing faster inference and reduced computational cost by removing the encoder, REM can generate text more efficiently, as the model only needs to process the input sequence once. This can be particularly beneficial in applications where speed is important, such as real-time chatbots or online translation services. For example, a chatbot using ReLLM would be able to respond to user queries more quickly than a chatbot using a traditional encoder-decoder architecture, which would need to encode the user query before generating a response. Challenge 1. Maintaining context and coherence across longer sequences. REM can struggle to maintain context and coherence when generating longer sequences, as the model's memory is limited. This can lead to the generated text becoming repetitive or incoherent, as the model may forget important information from the beginning of the sequence. For example, in a story generation task, REM might lose track of the plot or characters if the story is too long. Challenge 2. Preventing repetition and generating diverse outputs. REM can sometimes generate repetitive or predictable outputs, as the model is trained to predict the most likely next word in a sequence. This can be problematic in tasks where diversity and creativity are important, such as creative writing or generating novel ideas. For example, in a poem generation task, REM might generate the same rhyme scheme or use the same set of words repeatedly, resulting in a predictable and uninspired poem. LangchainExperimental, plan and execute. This section describes a tool called LangchainExperimental plan and execute, which leverages LangChain to generate and execute plans. This tool utilizes LangChain's capabilities in natural language processing (NLP) and integration with various external services to achieve automation. A tool that utilizes LangChain to generate and execute a plan This plan is generated using LangChain's natural language processing (NLP) capabilities. The tool enables users to describe a task in natural language, and LangChain can then translate that task into a sequence of steps, effectively creating a plan. After generating the plan, it utilizes LangChain's integration with external services to execute those steps, completing the task. For example, one could describe the task: write a blog post about the latest trends in artificial intelligence. And the tool would break down the task into steps such as research the latest trends in artificial intelligence, outline the blog post, write the blog post, edit the blog post, publish the blog post. Component 1. This refers to the LangChain experimental plan and execute component of LangChain, which is the core functionality of this tool. This component is responsible for generating the plan and executing it. Component 2. This component utilizes the LangChain LLMS library, which stands for Large Language Models, and is the foundation for LangChain's natural language capabilities. These language models are trained on massive amounts of text data, allowing them to understand and generate human-like text. This is used to enable the tool to understand and interpret the user's description of the task, effectively converting it into a sequence of steps. This tool is designed to automate tasks by generating plans and executing them. The key components of the architecture include the LangChain experimental plan and execute component for plan generation and execution, and the LangChain LLMS component for natural language understanding and generation. This tool aims to create a structured approach to problem solving by providing a framework for breaking down complex tasks into smaller, manageable steps. The primary role of this tool is to facilitate the execution of a sequence of actions based on a generated plan. This plan is essentially a set of steps that need to be taken to complete a given task. For example, if the task is to send a birthday email to a friend, the plan might include steps such as open email application, draft the email, attach a birthday greeting, and send the email. The tool then executes these steps in sequence, effectively automating the task. The tool provides a structured approach to problem solving by breaking down complex tasks into smaller, more manageable steps. This helps to ensure that the task is completed effectively and efficiently. It can be used to automate complex tasks, freeing up time and resources for other activities. By taking over repetitive or complex tasks, this tool can help to increase productivity and efficiency. Generating a plan for a complex task can be challenging, especially when there are multiple factors to consider and many possible steps involved. A significant challenge lies in understanding the nuances and intricacies of the task to ensure that the plan is comprehensive and effective. The tool's ability to generate a plan for a complex task depends on the quality and complexity of the underlying language model used. The execution of the plan may require specific tools or libraries. The plan may include steps that require access to specific application programming interfaces (APIs) or external tools. This can create challenges if the tool is not able to connect to these tools or if the tools are not readily available. The success of plan execution depends on the availability and reliability of external services and tools. LangChain experimental LLM functions, llama functions. A description of the LangChain experimental LLM functions, llama functions class and its components. A class that allows the use of llama functions within LangChain. Llama functions are a feature of the llama language model that allows for the execution of External tools and application programming interfaces (APIs) within the model's context. This class enables the integration of these functions within the LangChain framework, expanding the capabilities of language models by allowing them to interact with the real world through external resources. Component 1. LLM. This component refers to the underlying llama model, which is responsible for processing the input and generating responses. The model is used to execute the llama functions, providing the necessary context and knowledge for their execution. For example, if the llama function is designed to retrieve information from a weather API, the llama model would provide the necessary inputs, such as location and date, to the function and interpret the returned weather data. Component 2. Function caller. This component handles the actual execution of the llama function. It acts as an intermediary between the llama model and the external tool or API. The function caller ensures that the function is called correctly, passing the appropriate arguments and handling the returned results. For instance, if the function is designed to make a web request, the function caller would handle the actual communication with the web server, retrieving the requested data and passing it back to the llama model. Llama functions wraps an llama model and a function caller, enabling the execution of llama functions. The llama model provides the necessary context and knowledge for the function execution, while the function caller acts as the intermediary between the model and the external tool or API. This architecture ensures the seamless integration of llama functions within the LangChain framework, facilitates the integration of llama functions with LangChain, enabling the use of external tools and APIs within language models. This integration allows language models to interact with the real world, expanding their capabilities beyond simply processing text. For instance, a language model can use an llama function to retrieve information from a database, translate text into a different language, or even control a physical device. Advantage 1. Enables the use of llama functions within LangChain. The integration of llama functions within LangChain allows for the seamless execution of these functions within language model applications, expanding the capabilities of these models by enabling them to interact with external resources. This opens up new possibilities for language model applications, such as chatbots that can provide real-time information from external sources or writing assistants that can access databases to retrieve relevant information. Advantage 2. Extends the capabilities of language models by integrating external tools and APIs. By integrating external tools and application programming interfaces (APIs), language models can access a wide range of external information and functionality, expanding their capabilities beyond processing text. For example, a language model could use an API to access financial data to provide market analysis or user weather API to provide real-time weather information. This integration allows for the creation of more sophisticated and powerful language model applications that can interact with the real world in meaningful ways. Challenge 1. Requires an llama model and a function caller for proper functionality. The use of llama functions requires both an llama model and a function caller to operate. The model provides the necessary context and knowledge for the function execution, while the function caller acts as the intermediary between the model and the external tool or API. Ensuring that both components are properly configured and functioning is essential for the successful execution of llama functions. This requirement adds a layer of complexity to the implementation of llama functions within LangChain. Challenge 2. May need to handle llama function errors or failures. Like any other software, llama functions can encounter errors or failures during execution. These errors can be caused by a variety of factors, such as network connectivity issues, API errors, or incorrect input data. Handling these errors gracefully is crucial for the robustness of the system. This often involves implementing mechanisms to detect and handle errors, such as error handling code in the function caller or mechanisms for retrying failed function calls. Effective error handling ensures the reliable and consistent operation of llama functions within LangChain. LangChain experimental, plan and execute, executors, base, chain executor. A description of chain executor in the context of this YAML. Chain executor, a foundation for orchestrating large language model LLM-powered workflows. A foundational class for managing complex chains involving planning and execution. Provides a structured approach to handling asynchronous operations and monitoring task progress. Component 1. A component of the chain executor, a class that encapsulates the core logic of a chain executor. It orchestrates the planning and execution of LLM-powered workflows, managing the lifecycle of tasks and their dependencies. Component 2. A component of the chain executor, plan executor, a class responsible for generating execution plans based on the provided input and the chain structure. It determines the sequence of tasks, their dependencies, and the necessary resources for each step. Component 3. A component of the chain executor, execution result, a class used to track the progress and outcome of individual tasks within the workflow. It stores information such as the task status, e.g., pending, running, completed, failed, any errors encountered, and the results produced. A description of chain executor's architecture. Chain executor orchestrates planning and execution phases, leveraging plan executor for plan generation and managing tasks asynchronously. Execution result tracks task progress and outcomes. A description of chain executor's role centralizes the management of complex LLM-powered tasks by facilitating planning, execution, and monitoring. Advantage 1. A description of an advantage of using chain executor. Streamlined task management. Chain executor simplifies the management of complex workflows by providing a structured approach to planning, execution, and monitoring. This allows developers to focus on the logic of their LLM-powered tasks without needing to worry about the low-level details of task management. Advantage 2. A description of an advantage of using chain executor. Asynchronous execution for efficiency. Chain executor enables asynchronous task execution, allowing tasks to run in parallel and maximizing the utilization of resources. This leads to faster execution times for workflows, especially those involving computationally intensive LLM operations. Advantage 3. A description of an advantage of using chain executor. Transparent progress tracking. Chain executor provides real-time visibility into the progress of tasks within the workflow. Developers can easily monitor the status of each task, identify any potential bottlenecks, and track the overall completion progress of the workflow. Challenge 1. A description of a challenge of using chain executor. Managing complex task dependencies. Chain executor needs to handle intricate task dependencies, ensuring that tasks are executed in the correct order and that any required resources are available. This can be challenging when dealing with workflows involving multiple tasks and complex relationships between them. Challenge 2. A description of a challenge of using chain executor. Handling asynchronous execution errors. Asynchronous execution introduces the possibility of errors occurring during task execution. Chain executor needs to robustly handle these errors, preventing them from cascading across the workflow and potentially causing failures. Challenge 3. A description of a challenge of using chain executor ensuring consistent task completion. Chain executor must ensure that all tasks within the workflow are executed correctly and that the final result is consistent. This requires careful handling of potential failures, retries, and exception handling to maintain data integrity and avoid unexpected outcomes. Components. Definition. A component of langchainexperimental that orchestrates a sequence of actions to achieve a specific goal. The plan and execute agent is designed to handle complex tasks that involve multiple steps. Components. Agent. A core component of the plan and execute agent. It acts as an intermediary between the planner and the tool. It receives a plan from the planner and utilizes the tool to execute each step of the plan. For example, in a scenario where the task is to book a flight, the agent might interact with a travel booking tool to complete the booking process based on the provided plan. Tool. A specialized component that performs specific actions or operations. It receives instructions from the agent and interacts with external systems like APIs or databases. For example, in a flight booking task, the tool could be a travel API that interacts with different airlines to get flight options and prices. Planner. A critical component responsible for generating a sequence of actions that guide the agent to achieve the desired goal. It analyzes the task and determines the optimal steps to take. For example, the planner might analyze a flight booking request and generate a plan that involves searching for flights, comparing prices, and then finally selecting and booking a flight. Architecture. The plan and execute agent uses a modular approach, separating planning and execution. The planner, responsible for creating the plan, is independent of the agent, allowing flexibility in choosing different planning strategies. The agent, receiving the plan, executes it using the tool, ensuring that the desired outcome is achieved. For example, if you want to book a flight, the planner might create a plan that involves searching for flights based on your preferences and then booking the cheapest flight available. The agent would then execute this plan, using the Travel API tool to search for flights and then booking the chosen flight. Role. The plan and execute agent acts as a mediator between the user and the execution environment. It receives tasks from the user, plans the steps required to complete the task, and then executes those steps using the provided tool. For example, if you need to research a topic, the agent could be used to find relevant information on the internet. You could provide the agent with a topic to research, and it would use a web search tool to find relevant articles and websites. Advantages. The agent is capable of breaking down complex tasks into smaller manageable steps, making it easier to handle complex processes. For example, instead of trying to handle a complex booking process manually, the agent could handle the booking process by breaking it down into smaller steps. This makes the agent suitable for situations where tasks require multiple actions or involve interactions with different systems. The agent can be trained to improve its performance over time, by learning from past experiences and adapting to new information and tasks. This makes the agent more versatile and capable of handling a wider range of tasks. Challenges. The effectiveness of the plan and execute agent depends heavily on the quality of the plans generated by the planner. If the planner fails to create an effective plan, the agent will not be able to complete the task successfully. For example, If the planner provides a plan to book a flight that does not include the date of travel, the agent will be unable to complete the task. The agent relies on the tool to execute the plan. If the tool fails to execute a step correctly, the agent will not be able to complete the task. For example, if the travel API fails to find any available flights, the agent will not be able to complete the task. LangChain experimental, plan and execute, executors, base executor. Definition: base executor for plan and execute. This class serves as the foundation for executing planned steps within a task. It defines the core functionalities and structure for executing actions based on a predefined plan. It provides a standardized approach for handling various execution scenarios and ensures consistency across different implementations. Components. Component 1. LangChain experimental plan and execute planners base planner. This component represents the planner responsible for generating the plan of action. It determines the sequence of steps required to complete a task based on the given input and constraints. The base planner defines the core functionalities for planning, including goal setting, task decomposition, and step prioritization. Component 2. LangChain experimental plan and execute executors base executor. This component represents the executor responsible for carrying out the planned steps. It interacts with external systems, tools, or resources to execute each step in the plan. The base executor defines the core functionalities for execution, including step execution, error handling, and progress tracking. Architecture provides a framework to plan and execute tasks. This class employs a modular architecture that separates the planning and execution processes. This separation allows for independent development and customization of planners and executors, enabling flexibility in tailoring the system to different use cases and requirements. Role: handles the execution of planned steps. The base executor acts as the core component for carrying out the planned steps. It receives the plan from the planner and then executes each step in the prescribed order. It manages the interaction with external systems, handles any exceptions or errors encountered during execution, and reports the progress of the execution process. Advantages: modular execution of steps. The modular architecture enables the execution of each step independently, allowing for flexibility in adding, removing, or modifying steps within the plan. This modularity promotes code reusability and simplifies maintenance of the system. Flexibility to adapt to different execution contexts. This framework can adapt to various execution contexts and scenarios by providing a flexible structure for handling different tasks and environments. It allows for the customization of planners and executors based on the specific requirements of each task. Challenges: ensuring correct and reliable execution. The base executor must guarantee the accuracy and reliability of the execution process. This involves ensuring that each step is executed correctly, managing dependencies between steps, and mitigating potential errors or exceptions. Handling errors and exceptions during execution. The base executor must be robust enough to handle errors and exceptions that may arise during execution. This includes mechanisms for detecting errors, recovering from failures, and reporting exceptions to the user. LangChain experimental, plan and execute, planners, chat planner, planning output parser. Definition: planning output parser is a class within the LangChain experimental package that handles the task of parsing the output of a chat-based planner. Its core responsibility is to take the raw text output generated by the planner and transform it into a structured format. This structured format makes it considerably easier for downstream components within a LangChain pipeline to understand and process the information effectively. Components. Component 1. The planning output parser serves as a component primarily designed for parsing the output generated by chat-based planners. However, its functionality extends beyond chat-based planners. It can also be utilized for extracting structured information from the output of other planning methods. These methods encompass rule-based systems, which rely on a set of predefined rules to guide decision-making, and reinforcement learning techniques, where agents learn through trial and error to optimize their actions. Component 2. The planning output parser employs a combination of natural language processing (NLP) and machine learning techniques to extract meaningful information from the planner's output. NLP techniques, such as tokenization, part-of-speech tagging, and named entity recognition, are used to analyze the text and identify key entities, relationships, and actions. Machine learning models, trained on large datasets of planner outputs, can further enhance the parsing process by learning patterns and predicting the structure of pay. Output. Architecture. Planning output parser is typically integrated into a LangChain pipeline, a modular framework for building and executing complex AI applications. It seamlessly interacts with other components within the pipeline, such as chat-based planners, agents, and tools. The chat-based planner generates the initial plan. The agent executes the plan, and the tools provide specific functionalities to support the plan execution. Planning output parser plays a critical role in connecting these components by ensuring a consistent and structured flow of information. Role. The planning output parser plays a crucial role in bridging the gap between the unstructured output of a planner and the structured input expected by other components in the LangChain pipeline. This is particularly important in scenarios where the planner's output is in the form of natural language text. Planning output parser takes this unstructured text and converts it into a structured format, such as a dictionary or a list, that can be easily processed by other components in the pipeline. This ensures that the information generated by the planner is readily available to other components for further processing and action. Advantages. The planning output parser streamlines the process of handling output from chat-based planners by converting the raw text into a structured format. This structured format makes it significantly easier for downstream components to understand and process the information, simplifying the development of LangChain applications. The planning output parser's ability to convert unstructured output to a structured format significantly reduces the need for manual parsing and data cleaning, simplifying the development of LangChain applications. By automating this process, developers can focus on higher-level tasks, such as designing the overall architecture of the application and developing the logic of pay, planner and other components. Challenges. The accuracy of the planning output parser is directly influenced by the quality of the planner's output. If the planner's output is unclear, inconsistent, or poorly structured, the planning output parser may struggle to extract accurate and meaningful information. This emphasizes the importance of having a reliable and well-designed planner that produces high-quality output. Challenges arise when the planner's output is ambiguous or poorly structured. Ambiguity occurs when the text can be interpreted in multiple ways, leading to uncertainties in the parsing process. Poorly structured output, such as text with inconsistent formatting or missing information, can also pose difficulties for the planning output parser. In these cases, The planning output parser may require additional heuristics or contextual information to accurately parse the output. It may also benefit from incorporating techniques such as sentiment analysis or contextual awareness to better interpret the planner's output. LangchainExperimental, plan and execute, executors, base executor. Description of base executor. The base executor is a core class in the plan and execute paradigm. It serves as a blueprint for creating executors that manage the execution of plan steps. The base executor establishes a consistent structure for managing steps, executing tasks, and handling results. It defines fundamental methods and attributes for all executors, ensuring a unified approach to managing the execution flow. Description of components. Description of executor state attribute. The executor state attribute stores the current state of the execution. This includes the plan itself, the current step being executed, and the results obtained from the execution of previous steps. The executor state attribute is essential for tracking progress and ensuring the execution proceeds correctly. Description of execute step method. The execute step method is responsible for executing a specific step within the plan. It delegates the actual execution of the task defined in the step to a dedicated task runner. This method is crucial for orchestrating the execution of individual steps and ensuring proper updates to the executor state. Description of run method. The run method initiates the execution process, executing the steps defined in the plan sequentially. It uses the execute step method to execute each step and ensures the execution continues until the plan is completed. The run method is the primary entry point for starting the execution process. Description of architecture. The base executor class is designed for extensibility, providing a base framework for executors. This allows specific subclasses to implement custom logic for task execution, error handling, and result management. Subclasses can inherit from the base executor and override its methods to provide customized behaviors for specific use cases. Description of role. The base executor is a crucial part of the plan and execute paradigm. It provides a common foundation for managing the execution process, ensuring consistency and flexibility. The base executor ensures that steps are executed in a well-defined manner and that results are handled consistently. Description of advantages. Description of structured execution. The base executor offers a structured way to execute plans, enabling organized management of steps and results. This structure ensures that the execution process is well-defined and predictable, simplifying the management of complex plans. Description of modularity. The base executor promotes modularity by separating the plan definition from the execution logic. This separation enables the creation of customizable executors tailored to specific needs. Description of challenges. Description of extending base executor. The base executor needs to be extended with specific logic for managing task execution, error handling, and result management in subclasses. This extension is necessary to customize the behavior of executors for specific use cases, such as handling different types of tasks or implementing custom error recovery mechanisms. Description of robust execution logic. The base executor's execution logic needs to be robust enough to handle complex plans and diverse tasks. This robustness is essential to ensure that the base executor can manage a wide range of execution scenarios, including situations with complex dependencies between steps or tasks requiring different execution strategies. Summary of LangChain experimental LLMBashChain on-former decoder JSON-former. Nan, a decoder class for JSON-former. It is a specialized large language model LLM designed for interacting with JSON data structures. It focuses on tasks such as question answering and data extraction from JSON files. Component 1. JSON-former decoder is a crucial component of the JSON-former system. It is responsible for decoding and interpreting JSON data structures, allowing the LLM to understand and process the information within them. Component 2. The LLM wrapper acts as an intermediary between the JSON-former decoder and the underlying language model. It provides a layer of abstraction, allowing the JSON-former decoder to interact with the LLM efficiently and effectively. JSON-former decoder is built on top of LangChain, a framework designed to build and deploy applications powered by large language models (LLMs). It utilizes the capabilities of LLMs to process and comprehend JSON data structures. The JSON-former decoder serves as a specialized large language model LLM tailored for interacting with JSON data. It allows users to perform tasks such as retrieving specific information from JSON files, generating summaries from JSON data, and creating new JSON structures based on existing data. For example, it can be used to extract specific details from a JSON file containing product information, or to generate a summary of a JSON file containing news articles. JSON-former decoder offers enhanced performance for tasks involving JSON data. Its specialized design allows it to process JSON structures more efficiently than traditional LLMs, leading to faster response times and improved performance for various applications. For instance, if you need to extract information from a large JSON database of customer data, JSON-former decoder can process the data much faster than a general-purpose LLM. JSON-former decoder demonstrates improved accuracy in extracting information from JSON documents. Its specialized design and training process allow it to understand the structure of JSON data more effectively, leading to more accurate and reliable results when extracting information from JSON files. For instance, when extracting information from a JSON file containing scientific data, JSON-former decoder can provide more accurate results than a general-purpose LLM, ensuring that the extracted information is reliable and can be used for further analysis. JSON-former decoder may face limitations in handling complex JSON structures, particularly those with nested objects and arrays. These complex structures can pose challenges for the decoder, potentially leading to inaccuracies or difficulties in processing the data. For example, if a JSON file contains deeply nested objects with multiple layers of arrays, the decoder might struggle to process the entire structure effectively. The performance of JSON-former decoder can be affected by the quality of the underlying large language model LLM it uses. If the underlying LLM is not well trained or optimized for processing JSON data, it can lead to inaccuracies and limitations in the decoder's ability to handle JSON data effectively. This emphasizes the importance of choosing a high-quality and well-trained LLM for optimal performance of JSON-former decoder. For example, using a LLM that has been specifically trained on a large dataset of JSON documents could lead to significant improvements in the decoder's accuracy and performance. LangChain experimental, plan and execute, executors, base, chain executor. A deep dive into the LangChain executor. An abstract base class that serves as a foundation for all executors. It defines the core methods and behaviors that are shared by different executor implementations. Component 1. Chain executor. Plan and execute. A fundamental method that orchestrates the execution of a chain by first generating a plan using the configured executor and then executing the plan. Execute chain. A method for directly executing a chain without generating a plan. This allows for more direct control over the chain execution process. Get executor. Returns the executor currently configured for the chain executor. This allows for dynamic modification of the executor behavior. Set executor. A method used to configure the executor that will be used for planning and executing chains within the chain executor. Chain executor is a fundamental building block for working with chains in LangChain. It establishes a standardized approach to planning and executing chain sequences, regardless of the specific executor being used. The primary role of the chain executor is to provide a consistent interface for interacting with chains and their execution. This allows for easy integration and interchangeability of different executors within a LangChain application. The standardized interface provided by the chain executor ensures that all executors interact with chains in a uniform way, simplifying code and reducing the need for custom logic for each executor type. The ability to swap executors allows for flexibility in choosing the most appropriate execution strategy based on the specific requirements of the chain and the desired outcome. Creating custom executors requires a deep understanding of the LangChain framework and its underlying mechanisms. This can be challenging for developers who are new to LangChain or who are unfamiliar with the intricacies of chain execution. While chain executor is a powerful tool, it might not be suitable for all use cases, especially those that demand highly specialized or customized execution strategies. In such scenarios, developers may need to consider more tailored solutions or custom implementations. LangChain experimental plan and execute executors base executor summary. A comprehensive description of the base executor's purpose, components, architecture, role, advantages, and challenges. The base executor serves as the foundational class for all executors within the plan and execute framework. This class acts as a blueprint for defining executors, enabling the execution of various tasks through a unified approach. Component 1. The plan and execute method represents the core functionality of the base executor. It orchestrates the entire process of planning and executing tasks, providing a flexible and structured approach to task management. Component 2. The run plan method is an internal component responsible for executing the plan generated during the planning phase. It utilizes the plan's instructions to guide the execution of individual steps, ensuring a consistent and controlled process. The base executor's architecture revolves around the concept of separating planning and execution phases. This allows for efficient task management, facilitating the creation of complex workflows while maintaining a structured approach. The primary role of the base executor is to provide a standardized framework for implementing diverse plan and execute strategies. This framework enables developers to leverage a consistent interface for handling tasks, regardless of their complexity or execution method. Advantage 1. By providing a consistent interface for different planning and execution strategies, the base executor simplifies the development and integration of various task management solutions. This allows for seamless interaction between different executors, promoting reusability and modularity. Advantage 2. The ability to support both synchronous and asynchronous execution methods provides flexibility for different task requirements. Synchronous execution allows for sequential processing, while asynchronous execution enables parallel processing, optimizing resource utilization and maximizing efficiency. Challenge 1. Managing the complexity of planning and execution for diverse tasks poses a significant challenge. The base executor must handle tasks ranging from simple, single-step actions to intricate, multi-step processes. Balancing flexibility and efficiency in the face of diverse task complexity is crucial. Challenge 2. Ensuring efficient execution and resource utilization is essential for optimal performance. The base executor must optimize resource allocation and task scheduling to minimize execution time and maximize throughput. This includes considering factors such as resource availability, task dependencies, and execution constraints. LangChain experimental plan and execute schema step summarization. NaN. Plan and execute is a step that combines planning and execution within a single step. This step simplifies the process of creating and executing plans, making it more efficient. Imagine a robot tasked with cleaning a room. The plan and execute step would first use a planning tool to determine the optimal cleaning route, considering obstacles and the location of dirt. Once the plan is created, a chain of actions would be executed, such as moving to specific locations, picking up debris, and emptying the dustbin. Component 1. Plan and execute leverages a planning tool to generate a sequence of actions. The planning tool analyzes the problem, identifies relevant information, and suggests a series of steps to achieve the desired outcome. For example, a planning tool used for a travel itinerary might consider factors like budget, travel time, and preferred destinations to generate a sequence of flights, accommodation, and sightseeing activities. Component 2. Once a plan is created, it is executed using a chain, each step of which corresponds to an action in the plan. This chain acts as a sequence of instructions, each one representing a specific action to be performed. For example, a chain for preparing a meal might consist of steps such as chopping vegetables, cooking meat, and assembling the dish. The architecture of this step involves combining a planning tool and a chain for execution. This architecture allows for a structured and organized approach to problem solving. By separating the planning and execution phases, it ensures that the steps are well defined and efficient. For instance, a chatbot using plan and execute might first use a planning tool to understand the user's intent and then use a chain of responses to answer the query or complete the requested task. This step simplifies the process of creating and executing plans, making it more efficient. It enables a more structured and automated approach to problem solving by combining planning and execution within a single step. Imagine a customer service chatbot that uses plan and execute to handle customer inquiries. It would first use a planning tool to analyze the customer's question and then use a chain of responses to provide the necessary information or assistance. Advantage 1. Plan and execute provides a structured and organized approach to problem solving. By dividing the problem into manageable steps, it allows for clearer understanding, efficient execution, and better control over the process. Think of a project management tool that utilizes plan and execute. It would first generate a plan with tasks, deadlines, and dependencies. Then, a chain of actions would be executed, such as assigning tasks, tracking progress, and sending reminders. Advantage 2. It automates the execution of plans, minimizing manual intervention. Once a plan is generated, The execution can be automated, reducing the need for human involvement. This allows for faster completion, increased accuracy, and reduced human error. For example, a data analysis pipeline using plan and execute would generate a plan for data cleaning, transformation, and analysis. Then, the chain would automate the execution of these steps, reducing the chance of manual errors and ensuring consistency. Challenge 1. The accuracy and completeness of the planning tool can significantly impact the effectiveness of the execution. If the planning tool fails to accurately identify the problem, relevant information, or optimal steps, the execution may be ineffective or even produce unintended consequences. A weather forecasting system relying on plan and execute might generate a plan based on inaccurate weather data, leading to inefficient resource allocation or incorrect recommendations. Challenge 2. The chain used for execution may need to be customized to handle specific plan details. Different plans may require unique actions or sequences of actions, necessitating customization of the execution chain. An e-commerce platform using plan and execute might need different chains for processing different types of orders, such as pre-orders, regular orders, and bulk orders. LangchainExperimental Open Clip Summary. NaN. LangchainExperimental Open Clip is a powerful tool for connecting language and images through deep learning models. It leverages the Open Clip model, a pre-trained visual language model, to perform image text retrieval, image classification, and image captioning tasks. The LangChain framework provides an intuitive interface for interacting with OpenClip, allowing developers to easily integrate it into their applications. Component 1. LangChain is a framework for building and deploying applications powered by large language models, LLMs. It provides a set of tools and components that simplify the process of creating applications that utilize the power of LLMs. For example, developers can use LangChain to build chatbots, question answering systems, and text summarizers. Component 2. OpenClip is a pre-trained visual language model that can understand the relationship between images and text. It has been trained on a massive dataset of images and their corresponding captions, allowing it to learn associations between visual and textual concepts. This capability enables OpenClip to perform various tasks, such as retrieving images based on text descriptions, classifying images based on their content, and generating captions for images. The architecture of LangchainExperimental OpenClip involves combining the capabilities of LangChain and OpenClip. LangChain provides the infrastructure for defining tasks, retrieving data, and orchestrating interactions with OpenClip. OpenClip acts as the core component for understanding and processing images and text. LangchainExperimental OpenClip plays a crucial role in bridging the gap between the world of language and the world of images. It allows developers to build applications that can effectively analyze, understand, and generate both text and images. This opens up a wide range of possibilities for applications such as image search, visual question answering, and content creation. Advantage 1. Leveraging OpenClip's pre-trained capabilities reduces the need for extensive training data and computational resources. This is because OpenClip has already been trained on a large dataset, making it capable of performing various tasks without requiring further extensive training. This significantly reduces the time and resources required to build and deploy applications based on LangchainExperimental OpenClip. Advantage 2. LangchainExperimental OpenClip seamlessly integrates with LangChain's powerful framework for Building complex LLMBashChain applications. This integration allows developers to leverage the full capabilities of both LangChain and OpenClip, making it easier to build and deploy sophisticated applications. For instance, developers can utilize LangChain's features for prompt engineering and data retrieval to enhance OpenClip's capabilities in image-text tasks. Challenge 1. OpenClip models can be large, requiring significant computational resources for deployment and inference. This can pose a challenge for developers with limited computational resources, as deploying and running OpenClip models may require specialized hardware or cloud infrastructure. However, advancements in hardware and cloud computing are constantly making it easier and more affordable to utilize these large models. Challenge 2. Fine-tuning OpenClip for specific tasks may be necessary to achieve optimal performance, requiring additional training data and time. While OpenClip is a pre-trained model, it may not always perform optimally for every specific task. To achieve better performance, developers might need to fine-tune OpenClip on a dataset that is relevant to their specific application, which can require additional effort and resources. LangChain experimental PAL chain-based PAL validation. Definition. Detailed definition of the variable goes here. Components. Component 1. This is the first component of PAL validation. It is responsible for processing and analyzing the user's input, identifying the intent and entities within the request. For example, if the user asks what is the weather in London, component 1 would recognize weather as the intent, and London as the location entity. Component 2. The second component of PAL validation. It is responsible for validating the user's request against predefined constraints, and ensuring that the request can be fulfilled by the underlying system. This might involve checking if the requested information is available, if the user has the necessary permissions, or if PAL request is within the system's capabilities. For example, if PAL system doesn't have weather information for London, component 2 would identify this and provide appropriate feedback to the user. Architecture. Description of the architecture supporting the variable. This is the architecture of PAL validation. It is a pipeline architecture. The architecture leverages a chain of components, each performing a specific task, to process and validate the user's request. This modular approach allows for flexibility and extensibility, making it easier to add or modify components without affecting the overall system. Role. Explanation of the variable's role in the system. The role of PAL validation is to ensure the quality and validity of user requests before they are processed by the system. This includes checking for completeness, correctness, and compliance with system constraints, thereby enhancing the overall reliability and robustness of the system. Advantages. The first advantage of PAL validation is improved user experience by providing clear and informative error messages and feedback when a request is invalid. This helps users understand why their request was rejected and what steps they can take to correct it. The second advantage is enhanced system security by preventing malicious or unauthorized requests from reaching PAL system's core functionality. Challenges. The first challenge of PAL validation is maintaining a balance between comprehensive validation and avoiding excessive delays or user frustration. The second challenge of PAL validation is adapting to evolving user needs and system requirements, which may necessitate updates to the validation rules and processes. LangChain experimental prompt injection identifier, Hugging Face identifier, Hugging Face injection identifier. None. Definition. This class is designed to detect potential prompt injections in Hugging Face models. It uses a predefined set of keywords to identify potentially harmful prompts. For instance, if the user prompt includes keywords like system or eval, which are often used to execute arbitrary code in various programming languages, the class would flag it as a potential prompt injection. Components. Component 1. A list of keywords that indicate possible prompt injection attempts. This list can contain keywords associated with various programming languages, shell commands, or other potentially harmful functions. For example, keywords like import, OS, system, exec, or subprocess could be included to detect attempts to import external libraries or execute system commands. Component 2. A function to identify potential prompt injections in a given prompt. This function compares the user prompt against the list of keywords and raises a flag if any keywords are found. This function is essential for analyzing the user's prompt and determining if it contains any keywords that could be used for malicious purposes. Architecture. The class works by comparing the user prompt with the predefined list of keywords. If any keywords are found, the class raises a flag indicating a potential prompt injection attempt. This architecture relies on a simple keyword-based approach, which can be effective in catching basic prompt injection attempts. However, it may not be able to detect more complex or obfuscated injection attempts. Role. To enhance the security of Hugging Face models by identifying potentially harmful prompts that could be used to inject malicious code or data. In essence, this class acts as a safeguard against potential security breaches by analyzing user prompts and identifying potential code injections. Advantages. Helps prevent potential security breaches by identifying and flagging potential prompt injections. It acts as a first line of defense against malicious actors attempting to inject code into the model. Provides a simple and effective mechanism for detecting prompt injections. It offers a straightforward approach to security by relying on a predefined list of keywords and a simple comparison function. Challenges. The effectiveness of keyword-based detection is limited as it might not catch all types of prompt injections. More sophisticated prompt injection attacks might use obfuscation techniques or exploit vulnerabilities in the model's code that are not easily detectable through keyword matching. False positives might occur when the keywords are used in legitimate prompts. For instance, a prompt might contain a keyword like eval for a valid use case related to mathematical evaluation, not malicious code execution. False positives can lead to unnecessary blocking or delays in the application, requiring manual review of flagged prompts. LangchainExperimental, plan and execute. Schema, list step container. A container for steps to be executed in a plan. A container for steps to be executed in a plan. This container holds the steps that need to be performed to complete a specific task, arranged in a logical order for sequential execution. This allows for a structured and organized approach to task completion. Component 1. A list of steps to be executed. This list contains the individual actions or operations that need to be performed to achieve the overall goal. Each step represents a specific action that contributes to the completion of the plan. Component 2. A list of arguments to be passed to the steps. These arguments provide additional context and information to the steps, influencing how the steps are executed. For instance, an argument could be a specific file path or a set of parameters that modify the behavior of a step. The architecture of the list step container is a simple list of steps and arguments. It follows a straightforward linear structure where steps are executed one after the other. Each step is executed with its associated arguments, and the order of execution is determined by the position of the step in the list. The list step container's role is to provide a structure for executing a plan of steps. It acts as a container that holds the individual actions and their associated information, enabling the organized and sequential execution of a plan. It simplifies the process of managing and controlling the execution of a series of steps, ensuring that they are performed in the intended order and with the correct parameters. Advantage 1. Provides a simple and straightforward way to execute a plan. This simple structure is easy to understand and implement, making it suitable for plans that do not require complex logic or branching. It allows for a clear definition of steps and their execution order, contributing to plan transparency and predictability. Advantage 2. Allows for easy modification and extension of the plan. The list structure facilitates adding, removing, or modifying steps as needed. This flexibility makes it suitable for plans that may need to be adapted or adjusted based on changing requirements or new information. Challenge 1. The list step container does not provide any mechanism for handling errors or exceptions. If an error occurs during the execution of a step, the plan may terminate unexpectedly without proper error handling. This can lead to unpredictable behavior and potential data loss. Challenge 2. The list step container does not support any form of parallelism. All steps are executed sequentially, one after the other. This can be inefficient for plans that involve steps that can be executed concurrently. Parallel execution can significantly reduce execution time, especially for plans with computationally intensive steps. LangChain experimental plan and execute schema step. Definition. A step in the execution of a plan, utilizing LangChain's planning and execution capabilities. It involves specifying a plan, setting up tools for action, and providing a means to manage the execution flow. This step leverages LangChain's power for complex tasks that require a series of actions. For example, if you are trying to write a blog post, the plan would be to first brainstorm ideas, then research the topic, then write a draft, and finally edit and publish the post. Each step in the plan would involve specific tools, such as a language model for brainstorming, a search engine for research, a text editor for writing, and a publishing platform for publishing. Components. Component 1. LangChain's plan class provides a structure for organizing a series of steps, outlining the actions needed to complete a task. This class allows you to define the steps in your plan, the tools that will be used in each step, and the order in which the steps will be executed. For example, a plan to write a blog post might include steps like brainstorm ideas, research topic, write draft, and edit and publish. Component 2. Tools. A set of instruments or functions that the plan uses to execute actions. Examples include application programming interfaces (APIs), databases, and external systems. Tools allow the plan to interact with the real world and perform actions. For example, a plan to book a flight might use an API to search for flights, a database to store flight information, and an external system to make the reservation. Component 3. Executor manages the sequential execution of steps within the plan, ensuring proper order and handling of dependencies between actions. The executor ensures that the steps are executed in the correct order and that any dependencies between steps are handled properly. For example, the executor might make sure that the research topic step is executed before the write draft step, as the draft cannot be written without first researching the topic. Architecture. LangChain provides a foundation for planning and execution by offering components to define plans, connect to tools, and orchestrate actions. This framework allows for robust task management, particularly for complex, multi-step processes. For example, LangChain can be used to create a plan to write a blog post, book a flight, or generate a marketing campaign. Each plan would involve a series of steps, each with its own set of tools and dependencies. The framework allows you to define these steps, connect to the necessary tools, and manage the execution flow. Role. The plan and execute step acts as a central element in orchestrating complex actions. It facilitates breaking down tasks into a series of smaller steps, each with its own tool and execution logic. This modularity ensures that each step can be managed and executed effectively. For example, a plan to write a blog post could be broken down into the steps: brainstorm ideas, research topic, write draft, edit, and publish. Each step could then be assigned to a specific tool, such as a language model for brainstorming, a search engine for research, a text editor for writing, and a publishing platform for publishing. This modular approach allows you to easily manage the execution of each step, as well as the overall execution of the plan. Advantages. Decomposition breaks down complex tasks into smaller, manageable steps, facilitating easier planning and execution. By breaking down a complex task into smaller steps, you can more easily plan and execute it. For example, a plan to write a blog post could be broken down into the steps: brainstorm ideas, research topic, write draft, edit, and publish. This makes it easier to manage each step individually, as well as the overall execution of the plan. Modularity allows for the use of diverse tools and actions, offering flexibility in managing the execution process. By using different tools for different steps, you can achieve greater flexibility in managing the execution process. For example, a plan to write a blog post could use a language model for brainstorming, a search engine for research, a text editor for writing, and a publishing platform for publishing. This modular approach allows you to easily adapt the plan to different tasks and use the most appropriate tools for each step. Clarity provides a clear framework for understanding and monitoring the progress of a complex task. The plan and execute step provides a clear framework for understanding and monitoring the progress of a complex task. This is because each step is clearly defined, along with the tools that will be used and the dependencies between steps. For example, a plan to write a blog post would clearly outline the steps involved, the tools that will be used for each step, and the dependencies between steps. This makes it easier to understand the overall plan and to monitor the progress of the task. Challenges. Complexity. Managing intricate plans with numerous steps and dependencies can be challenging. As the number of steps and dependencies in a plan increases, the complexity of managing the plan also increases. For example, a plan to launch a new product might involve dozens of steps and dependencies. This can make it difficult to track the progress of the plan and to ensure that all steps are executed correctly. Error handling. Handling errors and unexpected situations during execution requires careful planning and robust error management mechanisms. Errors and unexpected situations can occur during the execution of a plan. These errors need to be handled in a way that does not disrupt the overall execution of the plan. For example, if a tool fails to complete a step in a plan, the plan should be able to handle this error and continue executing. Scalability. Scaling the plan and execution framework to handle large-scale tasks and complex Dependencies may require optimization as the scale of the task or the complexity of the dependencies increases. The plan and execution framework may need to be optimized to handle the increased load. For example, a plan to manage a large-scale marketing campaign might require optimization to handle the large number of steps and dependencies. Tool integration, integrating diverse tools and ensuring compatibility with the execution framework, can pose a challenge. The plan and execute framework needs to be able to integrate with a variety of tools. This can be a challenge, as different tools have different APIs and data formats. For example, a plan to write a blog post might need to integrate with a language model, a search engine, a text editor, and a publishing platform. Each of these tools has its own API and data format. So the plan and execute framework needs to be able to handle these differences. Debugging, diagnosing issues and debugging errors within the execution process can be complex due to the multi-step nature of the plan. Debugging errors within the execution process can be complex due to the multi-step nature of a plan. For example, if a step in the plan fails to execute correctly, it can be difficult to determine which step is causing the error. This is because the error could be caused by a problem with the tool used in that step, a problem with the data passed to the tool, or a problem with the dependency between that step and other steps in the plan. LangchainExperimental, prompt injection identifier, Hugging Face identifier, prompt injection exception. Summary: a custom exception class signifying a possible prompt injection attack during communication with a Hugging Face model. This exception serves as a safety measure, alerting developers to potentially malicious input that could manipulate the model's behavior. Component 1. This component represents the full name of the exception class. LangchainExperimental, prompt injection identifier, Hugging Face identifier, prompt injection exception. It's designed to be clear and descriptive for developers, clearly indicating the purpose and origin of the exception. Component 2. This component represents the module responsible for identifying prompt injection attacks within the context of Hugging Face models. It encapsulates the logic and methods used to detect potentially malicious inputs. This exception is a subclass of the general exception class, inheriting its core functionality. However, it specializes in indicating errors specifically related to prompt injection, providing more context for developers when debugging and handling errors. This exception plays a vital role in enhancing the security of interactions with Hugging Face models. It acts as a sentinel, detecting and raising an alarm when a potential prompt injection attack is identified. By flagging these attempts, it helps prevent malicious users from hijacking the model's responses or manipulating its behavior. This exception enhances the security of applications by proactively identifying potential injection attacks. This early detection allows developers to take immediate action, such as blocking the malicious input or logging the event for further investigation, minimizing the risk of successful attacks. This exception enables developers to handle prompt injection scenarios specifically, differentiating them from general errors. By isolating these cases, developers can tailor their error handling strategies to address the unique characteristics of prompt injection attacks, potentially leading to more effective and targeted mitigation measures. Implementing robust prompt injection detection requires a thorough understanding of the potential attack vectors. Developers need to carefully consider various techniques attackers might employ to manipulate prompts, such as code injection or data poisoning. This careful analysis is crucial for designing effective detection mechanisms that can identify a wide range of malicious inputs. Prompt injection detection systems, while powerful, are not always perfect. False positives, where legitimate inputs are incorrectly flagged as malicious, can occur. This necessitates a balance between sensitivity and accuracy. Developers must analyze the false positives, identify potential causes, and fine-tune the detection mechanisms to minimize these occurrences, ensuring the system remains effective while minimizing disruptions to legitimate users. Langchain-experimental PAL chain-based PAL validation. Definition: PAL validation is a component used for validating user inputs in the PAL chain. It ensures that the inputs provided by the user are valid and meet the expected format and requirements, thereby preventing errors and improving the overall quality of the results. For example, in a chatbot application, PAL validation can be used to verify that the user's input is in the correct format and that the user is asking a relevant question. Components. Component 1. PAL chain is a chain of components that work together to process user input and generate a response. It leverages the capabilities of a prompt-assisted learning PAL framework. Component 2. PAL, or prompt-assisted learning, is a framework that uses prompts to guide a language model in generating more relevant and informative responses. Architecture. PAL validation is designed to be integrated into the PAL chain, acting as a gatekeeper for user input. By validating the input, it ensures that the PAL chain can effectively process it and generate an accurate response. Role. PAL validation plays a crucial role in the PAL chain by acting as the validation component. It verifies the validity of the user's input, preventing the chain from processing invalid or inappropriate input and ensuring the accuracy and reliability of the generated responses. Advantages. By reducing the risk of invalid inputs, PAL validation increases the robustness of the PAL chain. It prevents the chain from encountering errors or generating incorrect responses due to invalid input, enhancing the overall reliability and stability of the system. By improving the accuracy of the results, PAL validation contributes to the overall effectiveness of the PAL chain. It ensures that the chain processes valid inputs and generates accurate and relevant responses, leading to a more satisfying and productive user experience. Challenges. Implementing PAL validation effectively can be challenging, as it requires careful consideration of the specific input validation rules and the potential edge cases. It is crucial to ensure that the validation rules are comprehensive enough to handle various input formats and scenarios while not being overly restrictive. PAL validation, while effective, can sometimes lead to false positives, where it incorrectly rejects valid input. This can happen if the validation rules are too strict or if the input format is not explicitly defined. It is essential to strike a balance between ensuring input validity and avoiding unnecessary rejection. LangChain experimental prompt injection identifier summarization. NaN. LangChain experimental prompt injection identifier is a mechanism used in LangChain to identify and isolate potential prompt injections. It allows users to safely execute code that can be provided as prompts in a LangChain application by isolating it from the application's main execution environment. For example, in a scenario where a user provides a prompt containing code snippets, the identifier would analyze the prompt and isolate the code snippets to execute them in a secure environment, preventing any potential malicious code from affecting the main application. Component 1. A function called identify injection that checks for potential prompt injection points in a given Input string. This function analyzes the input string for patterns that could indicate potential injection points, such as special characters or code keywords. For example, if the input string contains code snippets written in Python or JavaScript, the identify injection function would identify them as potential injection points and mark them accordingly. Component 2. The prompt injection identifier function, which utilizes the identify injection function to tag potential injection points in the input string, allowing LangChain to handle them safely. This function leverages the identify injection function to determine potential injection points and then tags them appropriately. This allows LangChain to isolate these injection points from the main application environment and execute them in a secure sandbox, preventing potential security vulnerabilities. The architecture of LangChain experimental prompt injection identifier utilizes a combination of string analysis and function calls to identify and handle potential prompt injection points. This architecture enables the identifier to effectively analyze user-provided prompts, identify potential injection points, and handle them safely. For instance, the identifier first uses string analysis techniques to scan the prompt for patterns indicating potential injection points, and then it uses the identify injection function to confirm and categorize these potential injection points. This approach ensures comprehensive identification and handling of potential injection points within user-provided prompts to enhance the security of LangChain applications by preventing malicious prompt injection attacks, isolating potentially dangerous code, and ensuring a safe execution environment. The identifier is a crucial component of LangChain's security framework, preventing potential attacks that could exploit vulnerabilities in the prompt handling process. It isolates potentially dangerous code, such as malicious scripts or commands, from the main application environment, ensuring that these scripts are not executed in the main environment and preventing any potential harm. Enhanced security by preventing prompt injection attacks. This advantage is crucial for maintaining the integrity and safety of LangChain applications by preventing malicious actors from exploiting vulnerabilities in prompt handling. For example, by preventing injection attacks, the identifier ensures that user-provided prompts are not manipulated to execute malicious code or access sensitive data, safeguarding the application and its users. Safely executing code provided as prompts. This advantage allows users to utilize code within prompts while maintaining a secure execution environment. For instance, a user could provide a prompt containing Python code to generate a text summary of a document. The identifier would isolate this Python code from the main application environment, execute it in a secure sandbox, and then return the generated text summary, ensuring safe execution of the code without compromising the application's security. Finding and classifying all potential injection points within a given string. This challenge involves accurately identifying all potential injection points in a given string, while avoiding false positives and ensuring comprehensive coverage. For example, the identifier needs to be able to recognize various programming languages, code snippets, and potentially malicious commands, even within complex user-provided prompts, ensuring that all potential injection points are correctly identified and handled. Balancing security with flexibility and user-friendliness. This challenge involves striking a balance between security measures and the ease of use and flexibility for users. For example, the identifier must be robust enough to prevent potential attacks, But it also needs to be flexible enough to accommodate diverse prompt formats and allow users to provide code snippets or complex commands without excessive restrictions. The goal is to provide a secure environment without hindering user experience or functionality. LangChain experimental plan and execute schema step response. None. The step response object represents the outcome of a single step in a plan. It contains information about the action taken, its status, any generated outputs, and any encountered errors. For example, if a step involves fetching data from an application programming interface API, the step response would contain the status of the API call successful, failed, or in progress, the data retrieved, and any errors encountered during the process. Component 1. The action that was taken during the step, usually described as a verb. For instance, the action could be fetch data, generate text, or execute code. Component 2 indicates whether the step was successful, failed, or is still in progress. This status provides a clear indication of the step's execution outcome. Component 3. The results generated by the action, which can be text, code, data, or any other relevant output. The output is the result of the action taken during the step. For example, if the action was fetch data, the output could be a list of articles fetched from a website. Component 4 contains details about any errors encountered during the execution of the step. This includes information about the error type, its message, and any other relevant details that can be used to diagnose and resolve the issue. This object is central to the plan and execute framework, serving as the building block for representing and managing the execution of a series of steps. It acts as a container for the information related to each individual step, allowing the framework to track the progress of the overall plan and manage the execution of individual steps. The step response object acts as a communication channel between the planning and execution phases. It provides a standardized format to track the progress of each step and communicate any relevant information back to the planner. The planner can use this information to make decisions about the next steps to be taken based on the outcome of the previous step. Advantage 1. Provides a clear and consistent representation of each step's outcome, enabling better monitoring and analysis of the execution process. This allows for a more accurate and insightful understanding of the plan's execution, making it easier to identify areas for improvement and optimize the plan's performance. Advantage 2. Facilitates error handling and debugging by providing detailed information about any encountered errors. This makes it easier to identify and troubleshoot problems during the plan's execution, allowing for more efficient resolution of any errors that occur. Challenge 1. Defining a comprehensive and flexible structure to accommodate the diverse outputs and error types across different steps and tools. This requires careful consideration of the various data formats and error types that may be encountered during the plan's execution, ensuring that the step response object is capable of capturing and representing all of this information accurately. Challenge 2. Ensuring consistent and meaningful interpretation of the step response object across different tools and use cases. This involves defining clear and consistent conventions for representing information in a step response object, so that it can be understood and interpreted correctly by different tools and applications. LangChain experimental PAL chain. Definition: a chain designed for building personalized AI assistants that can access external tools in application programming interfaces. It combines the capabilities of the personalized assistant language chain with the tool learning paradigm. Components. Component 1. Personalized Assistant Language Chain. PAL chain handles user interactions and manages the conversational flow. This component acts as the core of the assistant, engaging with users, understanding their requests, and maintaining the context of the conversation. For example, if a user asks for the weather, the PAL chain will first understand the user's intention and then utilize the appropriate tools to fetch the weather data. Component 2. Tool learning enables the chain to learn and utilize external tools, enhancing its capabilities. This component empowers the assistant to extend its functionalities beyond its inherent capabilities. For instance, if the user requests a summary of a news article, the tool learning component can identify and utilize a suitable tool like a summarization tool to fulfill the user's request. Architecture utilizes a combination of language models (LLMs), memory modules, and external tools to personalize interactions and fulfill user requests. The langchainexperimental PAL chain relies on a collaborative structure of components (LLMs) to understand and generate natural language, memory modules to retain conversational context, and external tools to perform specific tasks. This architectural blend allows the chain to provide personalized and informative responses to user inquiries. Role: to provide a framework for developing personalized assistants that can leverage external tools and adapt to user preferences. The langchainexperimental PAL chain aims to provide a foundation for building AI assistants that are tailored to individual users. It enables developers to create assistants that can learn user preferences, utilize external tools to accomplish complex tasks, and continuously improve their performance based on user feedback. Advantages: enhanced personalization tailors responses and actions based on user preferences. This capability allows the assistant to learn individual user habits, preferences, and interests. Consequently, it can offer personalized responses, tailor recommendations, and provide more relevant information to each user, creating a more engaging and valuable experience. Improved capabilities gains access to a wider range of functionality through tool integration. By integrating with external tools, the assistant can leverage functionalities beyond its inherent capabilities. For example, it can utilize tools for data analysis, code execution, or image recognition to provide more comprehensive and sophisticated answers to user queries. Challenges: managing tool selection, determining the most appropriate tool for a given request, selecting the right tool is crucial to ensure the assistant can fulfill the user's request effectively. This requires the chain to understand the user's intent and accurately identify the most relevant tool among the available options. Tool execution and error handling: handling potential errors during tool execution. When interacting with external tools, the assistant needs to handle potential errors that may arise during tool execution. This involves gracefully recovering from errors, providing feedback to the user, and potentially suggesting alternative tools or approaches to complete the task. Langchainexperimental, plan and execute. Schema: plan output parser. Plan output parser class in LangChain. The plan output parser class is a key component in LangChain's plan and execute module. It's designed to take the raw output generated by a plan execution process and transform it into a structured and easily digestible format. This class is crucial for making the results of a plan understandable and actionable for various applications. Components of plan output parser. Component 1. The plan output parser class utilizes a Python class to perform the conversion of plan execution output into a parsable format. This Python class serves as a central component that handles the interpretation and transformation of raw output, ensuring that the information is presented in a structured and readily usable manner. Component 2. Along with the Python class, the plan output parser class incorporates a set of dedicated functions designed specifically for parsing the output of plan execution. These functions work in tandem with the Python class to break down the raw output into its constituent parts, applying specific logic and rules tailored to the nature of the plan execution output. Architecture of plan output parser. The plan output parser class operates by taking the output of a plan execution, which typically consists of a list of dictionaries. Each dictionary represents a single step within the plan. The plan output parser class carefully examines each dictionary, extracting the relevant information and transforming it into a unified format, ensuring that the output is easily parsable and interpretable by other applications. Role of plan output parser. The primary responsibility of the plan output parser class is to bridge the gap between the raw output of a plan execution and the need for easily parsable and understandable information. It serves as a translator, taking the often complex and unstructured output of a plan execution and making it accessible in a format that can be readily used by other components or systems. Advantages of plan output parser. Advantage 1. The plan output parser class greatly simplifies the process of working with the output of plan executions. Instead of wrestling with raw and potentially unstructured data, users can leverage the plan output parser class to easily extract and analyze the results of their plans. This simplifies tasks like understanding the success or failure of a plan, analyzing key metrics, or extracting specific data points. Advantage 2. By providing a consistent parsing mechanism, the plan output parser class promotes uniformity and predictability in how plan execution outputs are handled, regardless of the specific nature of the plan or its output format. The plan output parser class ensures a consistent and reliable way to process the results, making it easier to build and maintain applications that rely on plan execution outputs. Challenges of plan output parser. Challenge 1. One of the challenges associated with the plan output parser class is its reliance on consistent output formats. If the output of a plan execution deviates significantly from a predictable format, the plan output parser class may struggle to effectively parse the information. This underscores the importance of maintaining consistent output formats for plan executions to ensure seamless integration with the plan output parser class. Challenge 2. The plan output parser class is designed to handle a wide variety of plan execution outputs. However, there may be instances where the output format is so unique or complex that the plan output parser class may not be able to adequately parse it. In such situations, it might be necessary to develop custom parsing logic or adapt the plan output parser class to handle the specific output format. Role. The vector SQL database chain retriever facilitates retrieving information from a database using natural language queries. It acts as a bridge between natural language and structured data, allowing users to query databases without writing SQL code. For example, a user could ask the vector SQL database chain retriever what is the average price of products in a electronics category, and the chain would translate this natural language query into an appropriate SQL query and retrieve the relevant information from the database. This eliminates the need for users to learn and write SQL code, making data retrieval more accessible and user-friendly. Advantages. enables querying structured data using natural language, eliminating the need for users to write SQL code. For example, instead of writing a complex SQL query, users can simply ask the vector SQL database chain retriever a question in natural language, such as what is the total number of orders placed in the last month? The chain will then translate this question into an appropriate SQL query and retrieve the desired information from the database. This eliminates the need for users to have any knowledge of SQL, making data access more accessible. Leverages vector SQL database to generate accurate SQL queries from natural language inputs. Vector SQL database uses advanced language models to understand the intent and meaning behind natural language queries and translate them into precise SQL queries. This ensures that the generated queries are accurate and efficient, leading to accurate and relevant information retrieval. For example, if a user asks what are the top 5 best-selling products, vector SQL database can accurately translate this query into a SQL statement that retrieves the top 5 products based on sales volume, providing the user with the desired information. Challenges: the vector SQL database component's ability to accurately translate natural language queries into SQL queries depends on the quality of the database schema and the training data used to fine-tune a model. The accuracy of the generated SQL queries depends on the quality of the database schema and a training data used for fine-tuning the vector SQL database model. A well-defined database schema helps the model understand the structure and relationships between different entities and attributes in the database, while comprehensive training data allows the model to learn various query patterns and accurately translate natural language queries into corresponding SQL statements. The retrieval process can be computationally expensive, especially for large datasets or complex queries. The retrieval process involves several steps, including embedding generation, similarity search, and SQL query generation, which can be computationally expensive, especially for large datasets or complex queries. This computational cost is particularly relevant when dealing with large datasets containing millions or billions of rows, where the retrieval process can be time-consuming and resource-intensive. Vector SQL database chain retriever. A description of the vector SQL database chain retriever with elaborated scalar values. A chain that uses vector SQL to retrieve relevant information from a database based on a user's query. Vector SQL is a tool that combines vector search and SQL query execution for efficient retrieval of data from a database. The retrieval chain utilizes vector SQL to find information based on a user's input, which can be in the form of a question, a statement, or a set of keywords. The chain interprets the user's query and uses vector SQL to search through the database for relevant information. The results are then presented to the user in a clear and concise manner. Component 1. LangChain's vector SQL retriever is a component of LangChain that enables the retrieval of information from a database using vector SQL. It acts as an interface between LangChain and vector SQL, allowing for seamless integration and retrieval operations. LangChain is a powerful framework for building and deploying language models. Component 2. A vector SQL database is a database system that supports both vector search and SQL query execution. This means that it can efficiently retrieve data based on both semantic similarity using vector search and structured queries using SQL. Vector search allows for finding data points that are similar to a given input vector, while SQL queries provide a structured way to access specific data based on defined criteria. The vector SQL database acts as the data storage and retrieval engine for the vector SQL database chain retriever. It uses the vector store for approximate nearest neighbor search in the SQL database for exact matches. The vector SQL database chain retriever leverages the power of both vector search and SQL query execution. The vector store is used for approximate nearest neighbor search, allowing for efficient retrieval of data points that are similar to the query. The SQL database is used for exact matches, ensuring that the retrieval process accurately captures all relevant information. This combination of search methods provides a robust and comprehensive approach to data retrieval. To retrieve information from a database using both vector search and SQL query execution, the vector SQL database chain retriever serves the purpose of retrieving information from a database by combining the strengths of vector search and SQL query execution. Vector search is used to find data that is semantically similar to the query, while SQL queries ensure that the retrieved data precisely matches the user's request. This dual approach enables the chain to handle a wide range of queries and retrieve information efficiently. It can handle both structured and unstructured data. The vector SQL database chain retriever is versatile and can handle both structured and unstructured data. This means it can retrieve information from databases containing structured data, such as tables and columns, as well as from databases that store unstructured data, such as text documents or images. This versatility makes the chain suitable for a wide range of applications, including knowledge retrieval, document search, and data analysis. It can leverage the benefits of both vector search and SQL query execution. The vector SQL database chain retriever harnesses the benefits of both vector search and SQL query execution. Vector search enables efficient retrieval of semantically similar data, while SQL query execution ensures precise and structured retrieval based on specific criteria. This combined approach allows for comprehensive and efficient retrieval of information, making the chain a powerful tool for data analysis and knowledge discovery. It can be challenging to configure and optimize vector SQL for specific use cases. Configuring and optimizing vector SQL for specific use cases can be challenging. The vector SQL database requires careful tuning of parameters to ensure optimal performance and accuracy for different data types and query patterns. This may involve adjusting indexing strategies, vector similarity metrics, and SQL query optimization techniques. It might be computationally expensive to run the retrieval. Running the retrieval process can be computationally expensive, especially for large databases and complex queries. The combination of vector search and SQL query execution can require significant processing power and time. This can be a challenge when dealing with real-time retrieval scenarios or when computational resources are limited. Langchainexperimental, llmbash, auto-selection scorer. Definition: a base class for auto-selection scorers. This class can be used to create a custom auto-selection scorer that leverages the rewards from a reinforcement learning agent. For instance, you could implement an auto-selection scorer that considers the historical performance of each tool in similar scenarios to determine the best tool for the current situation. Components. Component 1. A class that inherits from base auto-selection scorer and implements a score method that takes a list of tool-run objects and returns a score. This class defines the logic for evaluating the performance of different tools in a chain. The score method takes a list of tool run objects as input, representing the tools that have been run in the current chain. It then calculates a score for each tool based on its performance in the current context. Component 2. A list of tool run objects, representing the tools that have been run in the current chain. Each tool run object represents the execution of a tool, including its input, output, and execution time. This list provides the historical context for the auto-selection scorer, allowing it to evaluate the performance of tools based on their past performance in similar situations. Architecture. The architecture of auto-selection scorer is based on the idea of using reinforcement learning to learn a scoring function that can be used to select the best tool to use in a given situation. For example, the auto-selection scorer could learn that a certain tool is particularly effective for answering questions about a specific topic, or that another tool is better suited for generating creative text. Formats. The auto-selection scorer class provides a base implementation for this scoring function. Role. The auto-selection scorer is responsible for providing a score for each available tool based on the current state of the chain and the history of tool runs. For instance, given a chain that is currently in a state of needing to perform a specific task, the auto-selection scorer evaluates the available tools based on the current context and the history of tool runs to determine which tool is most likely to succeed in the current situation. This score is then used by the auto-selection agent to select the best tool to run next. Advantages. It can be used to create a custom auto-selection scorer that leverages the rewards from a reinforcement learning agent. This allows for more intelligent and adaptive tool selection, taking into account the specific context of the task and the history of tool runs. It is a flexible and powerful way to select the best tool to use in a given situation. It can be easily adapted to different types of chains and tools, allowing for a highly customizable and optimized tool selection process. Challenges. The implementation of the score method must be carefully designed to ensure that it is accurate and efficient. For instance, the score method needs to consider all relevant factors and provide a reliable assessment of tool performance, while also being computationally efficient to avoid delaying the execution of the chain. The auto-selection scorer must be trained on a large data set of tool runs in order to learn a good scoring function. This means that a sufficient number of tool run objects representing diverse scenarios and tool performances must be collected to ensure that the auto-selection scorer can accurately predict tool performance in future situations. langchainexperimental.palchain. Base. Palchain. A description of langchainexperimental palchain base palchain with explanations of its components. Architecture. Role. Advantages and challenges. A base class for palchains. This class provides the fundamental structure and methods for creating and using palchains, which are chains designed to execute a series of steps in a pipeline. Palchains leverage the call method to execute the chain, making them versatile for a range of tasks. Component 1. A chain that has a call method that takes a single input and returns a single output. This component is designed for straightforward tasks where a single input is processed to produce a single output. For example, a simple text summarization chain might take a paragraph of text as input and return a concise summary as output. Component 2. A chain that has a call method that takes multiple inputs and returns multiple outputs. This component allows for more complex operations where multiple inputs are processed simultaneously to generate multiple outputs. A scenario for this could be a chain that takes a list of documents and returns a list of their summaries. PAL chains are built on top of chains and use a call method to execute the chain. PAL chains are essentially specialized chains designed to streamline the execution of complex tasks. By breaking them down into a sequence of smaller steps, the call method plays a central role in executing these steps, making it the cornerstone of PAL chain operation. PAL chains are a type of chain that can be used to execute a series of steps in a pipeline. PAL chains act as powerful tools for building pipelines that automate complex processes. They enable you to define a sequence of steps, each representing a specific task, and execute them in a controlled and efficient manner. This is analogous to a production line where each step contributes to the final product. PAL chains are easy to use and can be used to execute complex pipelines. PAL chains simplify the creation and execution of complex workflows by providing a structured and intuitive framework. They abstract away the complexities of managing individual steps and allow you to focus on overall pipeline logic, making them ideal for tasks that require a series of interconnected actions. PAL chains are modular and can be easily extended to support new features. The modular nature of PAL chains enables you to build flexible and customizable pipelines. You can readily add new components, modify existing ones, or rearrange the order of steps to adapt to evolving requirements. This extensibility ensures that your pipelines remain relevant and adaptable over time. PAL chains can be difficult to debug. Debugging PAL chains, particularly those with complex pipelines, can be challenging due to the intricate interplay of multiple components. Understanding the flow of data and identifying the source of errors might require careful examination of each step and their interactions. PAL chains can be slow to execute. The execution speed of a PAL chain depends on the complexity of the pipeline and the computational demands of individual components. In scenarios involving multiple steps, resource-intensive operations, or large data sets, the overall execution time can be substantial. Optimization techniques and efficient resource management are crucial for mitigating performance bottlenecks. LangChain experimental RL chain base event. Definition. A detailed definition of the LangChain experimental RL chain base event variable. The LangChain experimental RL chain base event is a fundamental component of the reinforcement learning RL chain, designed to encapsulate and manage information pertaining to each step within the RL chain's execution. The LangChain experimental RL chain base event comprises two key components. 1. Component 1, a base event used to store information about a step in the RL chain. This component serves as the primary container for all the crucial data related to a specific step within the RL chain. It acts as a chronicle of the decisions made, the actions taken, and the outcomes observed during that particular step. Imagine this as a logbook meticulously documenting every move and consequence of an ongoing journey. In this case, the RL chain's learning process. 2. Component 2. This event is then used to update the RL chain's state. This component leverages the information gathered in component 1 to update the overall state of the RL chain. Think of it as a continuously evolving map, updated with each new piece of information recorded in the base event. This dynamically changing state reflects the learning progress of the RL chain, guiding its future decisions and actions. Architecture. A detailed description of the architecture supporting the LangChain experimental RL chain base event. The architecture of the LangChain experimental RL chain base event is fundamentally built on the concept of an object that represents a step in the RL chain. This object acts as a snapshot of the RL chain's state at a specific point in time, providing a detailed account of the actions taken and the subsequent rewards received. It serves as a cornerstone of the RL chain's internal workings, enabling it to learn and adapt based on its experiences. Think of it as a building block that, when put together with other similar objects, forms the complete picture of the RL chain's execution. Each object contains information about the context, the decision-making process, and the feedback received, allowing the RL chain to learn from its past and optimize its future actions. Role: an explanation of the LangChain experimental RL chain base event's role in the system. The role of the LangChain experimental RL chain base event is crucial in the functioning of the RL chain. It serves as the memory of the RL chain, storing detailed information about each step of its learning process. Imagine this as a detailed record of each decision made, action taken, and the subsequent reward received. This information is then used by the RL chain to refine its strategies and improve its performance. Over time, this event essentially forms the basis for the RL chain's learning process, allowing it to build upon past experiences and continually evolve its behavior. This constant updating and refinement of the internal state is what drives the learning and improvement in the RL chain. Advantages. Advantage 1. A detailed explanation of the first advantage of using the LangChain experimental RL chain base event. The primary advantage of employing the LangChain experimental RL chain base event is its ability to enhance the understanding of the RL chain's behavior. By providing a comprehensive record of each step, the event acts as a transparent window into the RL chain's decision-making process. It allows researchers and developers to analyze the RL chain's actions and understand the reasoning behind them. This deep dive into the RL chain's internal workings provides valuable insights, paving the way for targeted improvements and optimizations. For instance, analyzing the event log might reveal that the RL chain is struggling with certain types of situations, leading to the development of specific strategies to address these challenges. Advantage 2. A detailed explanation of the second advantage of using the LangChain experimental RL chain base event. Another significant advantage of using the LangChain experimental RL chain base event is its contribution to the ease of debugging and optimizing the RL chain. The detailed information captured in the event serves as an invaluable resource for identifying and resolving issues within the RL chain. By analyzing the event log, developers can pinpoint specific steps where the RL chain is performing suboptimally, leading to targeted interventions and improvements. Additionally, the event log provides a clear and concise record of the RL chain's progress, enabling developers to track the effectiveness of various optimization strategies. Imagine this as a detailed report card of the RL chain's performance, allowing developers to adjust and fine-tune the system for optimal results. Challenges. Challenge 1. A detailed explanation of the first challenge of using the LangChain experimental RL chain base event. One of the primary challenges associated with the LangChain experimental RL chain base event is the need for its continuous updating as the RL chain progresses. The information stored in the event needs to be consistently updated to reflect the changing state of the RL chain. This requires robust mechanisms to ensure that the event is accurately and efficiently updated with each step of the RL chain. The event should be able to adapt and evolve in real time, capturing the dynamics of the learning process. This is similar to managing a dynamic database where information is continuously added, updated, and retrieved to keep track of the evolving state of the RL chain. Challenge 2. A detailed explanation of the second challenge of using the LangChain experimental RL chain base event. Another challenge associated with the LangChain experimental RL chain base event is ensuring that the event is stored in a manner that is easily accessible and searchable. As the RL chain progresses, the number of events recorded grows significantly, requiring an efficient storage and retrieval system. The event data needs to be readily available for analysis and retrieval, enabling researchers and developers to access the necessary information for understanding RL chain's behavior and making informed decisions. This requires a well-designed storage system that balances efficiency with accessibility, allowing for quick and easy access to the relevant information while ensuring the integrity of stored data. Think of it as building an extensive library of knowledge about the RL chain, making sure that any desired information can be found easily and efficiently. LangChain experimental RL chain base selected. Definition. This is a base class for RL chains. RL chains are a way to use reinforcement learning to train language chains to perform a specific task. For example, you can train a language chain to summarize documents by rewarding it for producing concise summaries that accurately capture the main points of the text. Components. Component 1. Reinforcement learning agent. Component 2. LangChain. Architecture. The selected class inherits from the RL chain class. The selected class is a subclass of RL chain, meaning it inherits all of the functionality of RL chain. This class implements the logic for selecting the best action to take at each step of the task. Role. The selected class is responsible for selecting the best action to take at each step of the task. The selected class uses the RL agent to make decisions about which action to take at each step of the task. Advantages. Flexibility can be used with a variety of reinforcement learning agents. For example, you can use a deep Q network DQN or a proximal policy optimization PPO agent. Efficiency can be trained to perform tasks quickly and efficiently. For example, you can train a language chain to generate summaries in a fraction of the time it would take a human to do so. Challenges. Complexity. Setting up and training an RL chain can be complex. It requires understanding of the RL agent, the task, and the training data. Performance. The performance of an RL chain can be highly dependent on the quality of the training data and the choice of reinforcement learning agent. Poor training data can lead to poor performance, and a poorly chosen RL agent may not be able to learn the task effectively. LangChain experimental RL chain base policy. Definition. This describes the foundation of reinforcement learning chains within the LangChain framework. It sets the basic structure and features shared by all reinforcement learning chains. Components. Component 1. The policy attribute acts as the core of the reinforcement learning process. It decides which actions to take based on the current state of the chain. Imagine this like a decision maker in a game, choosing the next move based on the current game situation. Component 2. The reward FN attribute is responsible for evaluating how good a chain's action was. It assigns a numerical score based on the chain's performance. This score guides the learning process, indicating whether the chain's actions led to success or failure. Think of it as a judge in a competition, giving points for good performance and deducting points for mistakes. Component 3. The observation FN attribute translates the chain's internal state into a format that the policy can understand. It's like a translator, making sure the decision maker, the policy, can understand the complex language of the chain's internal Situation. Architecture. The base policy class acts as a blueprint for all reinforcement learning chains. It eliminates the need to reinvent the wheel for common elements, allowing developers to focus on creating specific policies for different tasks. It's like a building plan for different types of houses, providing the basic framework while allowing for unique customizations. Role. This base policy class is crucial for constructing custom reinforcement learning chains. It defines the key components responsible for policy-driven action selection, reward calculation, and representing the state of the chain. It's like the foundation of a house, providing the essential elements for building a sturdy and adaptable structure. Advantages. This structured approach to implementing reinforcement learning chains in LangChain encourages code reusability and maintainability. It's like having a set of pre-designed parts for a machine, making it easier to build and repair. The encapsulation of core reinforcement learning components simplifies the development of complex reinforcement learning applications. It's like having pre-built modules for a software application, allowing developers to focus on the specific logic without worrying about the underlying details. Challenges. This approach requires defining specific reward functions and observation functions tailored to the task. It's like crafting a set of rules and measurements specific to a game, ensuring the system can evaluate performance accurately. Finding the optimal policy parameters for effective performance may require extensive experimentation. It's like tuning the settings of a machine to find the best configuration for achieving its goals. Langchainexperimental, RL-chain, base, VW policy summary. This is a summary of the VW policy used in reinforcement learning chains. A policy used in reinforcement learning chains for choosing actions based on the current state and the provided reward function. This policy is typically used in conjunction with a value function that estimates the expected future reward for each state. The VW policy selects the action that maximizes the expected future reward based on the current state and the reward function. Component 1. A reward function that provides a numerical score for each action taken in a given state. This function is crucial in guiding the agent's learning process. It assigns a numerical value to each action based on its desirability in a particular state. For instance, in a game, the reward function might assign positive values to actions that lead to winning the game and negative values to actions that lead to losing. Component 2. A state representation that captures the relevant information about the current state of the environment. The state representation should be informative enough to allow the agent to make informed decisions about actions to take. For example, in a self-driving car, the state representation might include the car's speed, position, and the positions of other vehicles. Component 3. An action space that defines the set of possible actions that can be taken in a given state. The action space is crucial for determining the range of actions available to the agent. In a robotic arm, for instance, the action space might include the arm's joint angles or the velocity of its gripper. The VW policy uses a value-based approach to reinforcement learning, where the policy is derived from a value function that estimates the expected future reward for each state. In value-based reinforcement learning, the agent learns a value function that assigns a value to each state based on its expected future reward. The policy then selects the action that maximizes the value function in the current state. This approach is particularly useful when the state space is relatively small, as it allows the agent to efficiently learn the optimal policy. The VW policy is used to select the action that maximizes the expected future reward based on pay, current state, and the reward function. The VW policy uses a value-based approach to reinforcement learning, where the policy is derived from a value function that estimates the expected future reward for each state. The agent learns a value function that assigns a value to each state based on its expected future reward. The policy then selects the action that maximizes the value function in the current state. This approach is particularly useful when the state space is relatively small, as it allows the agent to efficiently learn the optimal policy. It can learn to take optimal actions in complex environments with high-dimensional state spaces. This is because the VW policy is able to learn the value function for each state, which allows it to choose the optimal action based on the current state and the expected future reward. For example, in a game like Go, the state space is incredibly large. But the VW policy can still learn to play optimally by using a value function to evaluate different game positions. It can be used to solve a wide range of reinforcement learning problems, including control, optimization, and game playing. The VW policy is a general-purpose reinforcement learning algorithm that can be applied to a variety of problems. For example, it can be used to control robots, optimize resource allocation, or play games. It can be difficult to tune the hyperparameters of the reward function and value function. The performance of the VW policy is highly dependent on the choice of hyperparameters, such as the learning rate and the discount factor. Finding the optimal hyperparameters can be a challenging task, which often requires extensive experimentation. It can be computationally expensive to train a value function for complex environments. The computational cost of training the value function increases significantly with the size of pay state space. In complex environments with large state spaces, training the value function can be computationally expensive and may require significant computing resources. Components. Definition. A reinforcement learning chain that utilizes a LangChain agent to engage with the environment. The chain aims to learn and optimize its actions within the environment through trial and error by receiving feedback in the form of rewards or penalties. This allows the agent to gradually improve its performance over time. Components. Agent. A LangChain agent that interacts with the environment. The agent acts as an intermediary, receiving information from the environment and translating it into instructions for the language model. It then receives responses from the language model and executes them within the environment. For example, in a game, the agent might be responsible for taking actions based on the current state of the game, such as moving pieces or attacking opponents. Reward function. A function that takes an observation and an action and returns a reward. The reward function provides feedback to the agent, indicating how well its actions are performing. For example, in a game, the reward function might give a positive reward for winning a round and a negative reward for losing. The agent uses this feedback to adjust its strategies and optimize its performance. Environment. The environment that the agent interacts with. The environment is the context within which the agent operates and learns. It can represent various scenarios, such as playing a game, controlling a robot, or engaging in natural language conversations. For example, in a game, the environment would be the rules of the game, the game board, and the other players. Memory. An optional memory to store past observations and actions. The memory allows the agent to learn from its past experiences and use this knowledge to improve its future decisions. For instance, In a game, the agent could remember previous winning strategies or identify patterns in the opponent's behavior. LLM, a language model to generate actions. The language model is responsible for generating actions based on the agent's observations and instructions. For example, in a game, the language model might suggest the best move to make based on the current game state. Architecture. The chain is composed of an agent that interacts with the environment. The agent uses a language model to generate actions and a reward function to evaluate the actions. The chain can optionally use a memory to store past observations and actions. The agent's interaction with the environment, combined with the reward function's feedback, allows the agent to learn and adapt its actions. Role. The chain is designed to solve problems in environments where the agent needs to learn from its interactions with the environment. It is particularly suitable for complex scenarios where predefined solutions are not feasible or where the optimal strategy might change over time. For example, in a game, the agent could learn to play against different opponents with different styles. Advantages can be used to solve a wide range of problems, including games, robotics, and natural language processing. The flexibility of the chain makes it applicable across various domains, from entertainment to industrial automation. For instance, in robotics, an agent could learn to navigate a complex environment or perform intricate tasks. Can learn from its interactions with the environment and improve its performance over time. This ability to learn from experience is one of the key advantages of reinforcement learning. The agent can continually adapt its actions based on new information, leading to better performance over time. Challenges can be difficult to design and train, especially for complex environments. The process of designing and training a reinforcement learning chain can be challenging, especially for complex environments with numerous states, actions, and rewards. It requires careful selection of appropriate components, such as the agent, reward function, and language model, as well as effective training algorithms. May be computationally expensive to run. Especially for large environments, reinforcement learning can be computationally intensive, particularly for large environments with many possible states and actions. This can require significant processing power and time to train the agent effectively. Langchain experimental RL chain base event. Definition. Detailed definition of the langchain experimental RL chain base event variable. It encapsulates a single step in the reinforcement learning RL training process, providing a structured representation of the interactions between the agent and its environment. This variable is crucial for understanding the dynamics of the training process and making informed decisions about the agent's actions. Components. Component 1 represents a single step in the RL training process. It captures the state of the agent and its environment, the action chosen by the agent, the reward received for that action, and the resulting new state of the environment. This information is crucial for learning and improving the agent's behavior over time. Component 2 contains information about the current state of the agent, the action taken, the reward received, and the next state. This information is essential for training the RL agent effectively. By recording each interaction, the agent can analyze its past actions, understand the consequences of its choices, and adapt its behavior for future situations. Architecture. Description of the architecture supporting the langchain experimental RL chain base event variable. The langchain experimental RL chain base event variable plays a fundamental role in the architecture of reinforcement learning RL algorithms. It provides a structured way to represent and Manage the data that drives the training process. Each event represents a single interaction between the agent and its environment, allowing RL algorithms to learn from these interactions and improve their performance. This variable is essential for understanding the dynamics of the RL system and for guiding the learning process. Role. Explanation of the LangChain experimental RL chain base event variable's role in the system. This variable is essential for training an RL agent by providing feedback on its actions and guiding it towards optimal behavior. It acts as a key component of the learning loop, allowing the agent to learn from past experiences and adjust its actions accordingly. The event variable serves as a central repository for information about each interaction, enabling the agent to analyze its performance and make informed decisions about future actions. Advantages. Provides a structured way to store and process information during RL training. The LangChain experimental RL chain base event variable offers a standardized format for representing training data, making it easier to manage, analyze, and process information effectively. This structured approach simplifies the implementation of various RL algorithms and facilitates efficient data analysis. Facilitates the implementation of various RL algorithms. By providing a standardized format for training data, the LangChain experimental RL chain base event variable significantly simplifies the implementation of various RL algorithms. This variable allows different algorithms to seamlessly access and utilize the same data format, promoting code reusability and reducing development time. Challenges. Ensuring proper data representation and handling of complex state spaces. A key challenge in implementing the LangChain experimental RL chain base event variable is ensuring that it can accurately represent the complex state spaces and actions involved in RL scenarios. For example, handling continuous state variables, multidimensional action spaces, and complex reward functions requires careful design and implementation. Optimizing the storage and retrieval of events for efficient training. Another challenge lies in optimizing the storage and retrieval of events to ensure efficient training. As RL training often involves large amounts of data, it is critical to design efficient storage mechanisms and retrieval algorithms that can quickly access relevant information. This requires careful consideration of the data structures used, the indexing methods employed, and the overall system architecture. LangChain experimental prompt injection identifier. A detailed explanation of the LangChain experimental prompt injection identifier feature. Its purpose, components, architecture, role, advantages, and challenges. A LangChain experimental feature that aims to identify potential prompt injection vulnerabilities. In chains, prompt injection is a security vulnerability that occurs when an attacker can inject malicious code into a prompt that is used by a language model. This can lead to the language model executing unintended or harmful actions. For example, an attacker could inject a malicious prompt into a chain that is used to generate code. The language model could then generate code that executes the attacker's malicious code, potentially compromising the system. This feature helps mitigate these risks by analyzing prompts for potential vulnerabilities. Component 1. An analysis function that inspects the chain's prompt template for potential injection risks. This component scrutinizes the structure of the prompt template, searching for patterns that could potentially enable malicious input injection. It analyzes the way user input is integrated into the prompt, looking for signs of potential manipulation or exploitation. For instance, if the prompt template directly includes user input without sanitization or validation, It could be vulnerable to injection attacks. This component aims to flag such vulnerabilities. Component 2. A set of rules and patterns designed to detect common prompt injection vectors. These rules and patterns act as a safety net, identifying common tactics used by attackers to inject malicious code into prompts. They encompass various methods like SQL injection, cross-site scripting XSS, and other vulnerabilities that can be exploited through prompts. This component serves as a proactive measure, aiming to prevent these known vulnerabilities from being exploited. The identifier is integrated into the chain's execution process, analyzing the prompt template before and during execution. It operates as a built-in security measure, examining the prompt template throughout the execution process. This ensures that the prompt security is assessed at every step, before and during the execution of the chain. For example, if the prompt is dynamically generated based on user input, the identifier would analyze the prompt at each stage of its construction, guarding against potential injection vulnerabilities. It acts as a security measure to identify and potentially mitigate vulnerabilities that could lead to malicious prompt injection attacks. The LangChain experimental prompt injection identifier acts as a defense mechanism against prompt injection attacks. It aims to prevent malicious code from being executed by the language model, ensuring the integrity and security of the system. For instance, if the identifier detects a potential injection vulnerability, it could either flag the issue for human review or, in certain cases, automatically sanitize the prompt to prevent the execution of malicious code. Early detection of prompt injection risks. The prompt injection identifier proactively scans for potential vulnerabilities, allowing for early detection of risks. This proactive approach helps identify and address potential vulnerabilities before they can be exploited by attackers. Early detection is critical to mitigating security risks and protecting systems from harm. Potential for mitigating vulnerabilities. The identifier aims to not only detect vulnerabilities but also to potentially mitigate them. It can either flag the issue for human review or, in certain cases, automatically sanitize the prompt to prevent the execution of malicious code. Mitigation is a key aspect of security, reducing the impact of vulnerabilities and protecting the system from attack. False positives due to complex prompt structures. Complex prompts, particularly those involving dynamic generation or intricate logic, can sometimes trigger false positives. The identifier might misinterpret certain patterns as vulnerabilities, leading to unnecessary warnings. This can create a challenge in balancing security with usability, as false positives can lead to disruptions and unnecessary human intervention. Limited scope in detecting all injection vectors. The identifier, while comprehensive, may not be able to detect all possible injection vectors. Emerging attack techniques or complex vulnerabilities might escape its detection mechanisms. The continuous evolution of attack tactics necessitates ongoing refinement and improvement of the identifier to ensure its effectiveness in combating evolving security threats. LangChain experimental RL chain-based selection scorer. Definition. Defines how to score the selected output from the chain during training. This class implements a selection scorer that can be used to evaluate the quality of the chosen output during training. Components. Component 1. Init self, selection scorer callable triple dot float initializes the selection scorer with a selection scorer function. The selection scorer function should accept the following arguments: observation, the observation from the environment; action, the action taken by the agent; chosen output, the chosen output from the chain; All outputs, a list of all outputs from the chain. Component 2. Score self, observation, dict, action, dict, chosen output, str, all outputs, list bracket, open str bracket, close right arrow float scores the selected output. Architecture. This class is a simple wrapper around a callable function that defines the selection scorer. The selection scorer function is used to evaluate the quality of the chosen output during training. Role. The selection scorer plays a crucial role in the training process of the RL chain. It provides a way to evaluate the quality of the chosen output from the chain based on pay, observation and action taken. This evaluation helps the agent learn to select the best output for a given situation. Advantages. Flexibility. The selection scorer can be customized to evaluate different aspects of the chosen output. For example, in a chatbot, the selection scorer could be customized to evaluate the output based on its relevance, clarity, and informativeness. Customizability allows defining a specific scoring function tailored to the needs of the application. This can be useful in situations where the standard scoring functions are not sufficient to evaluate the quality of the output. For example, if the application requires a specific type of output, such as a code snippet, the selection scorer can be customized to evaluate the output based on its syntax and functionality. Challenges. Complexity. Defining an effective selection scorer requires careful consideration of pay, application-specific requirements. It is important to choose a selection scorer that accurately reflects the desired outcome of pay. Training process. A poorly chosen selection scorer can lead to suboptimal performance. The selection scorer should be efficient to avoid slowing down the training process. A complex selection scorer can increase the time required to train the agent. It is important to strike a balance between accuracy and performance when choosing a selection scorer. LangChain experimental RL chain-based selection scorer. Description of LangChain experimental RL chain-based selection scorer. A base class for selection scorers in the reinforcement learning RL chain. The selection scorer is an integral component of the RL chain architecture, which facilitates the creation and implementation of reinforcement learning agents within PAY. LangChain framework. Description of components. Description of component 1. This abstract class serves as the foundation for selection scorers within the RL chain. It defines the core structure and methods common to all selection scorers, providing a standardized interface for interaction with the RL chain. For example, the selection scorer could be used to choose the best prompt to send to a language model in order to get the most relevant response. Description of component 2. This component outlines the interface for scoring the selection of different actions within PAY. RL chain. It defines the expected behavior of selection scorers, including methods for calculating scores for each action and providing a mechanism for the RL chain to access these scores. For instance, the RL chain could use this interface to determine the best course of action by comparing the scores of different actions. Description of architecture. The selection scorer plays a crucial role in the RL chain architecture. It evaluates the quality of different action choices, providing valuable feedback to the RL chain's decision-making process. This feedback helps guide the RL chain towards optimal decision-making, optimizing its performance over time. In a real-world example, the selection scorer might be used to choose the best approach to answering a complex question by considering various knowledge sources and reasoning strategies. Description of role. The primary role of the selection scorer is to assess the desirability of each potential action. Within the RL chain, the scorer's output is used by the RL chain to inform its decision making, determining which action to take in a given situation. This process is analogous to a human expert evaluating different options and choosing the best course of action based on their expertise and the current context. Description of advantages. Description of advantage 1. The selection scorer offers a flexible framework that allows for the integration of various scoring strategies, providing a mechanism to customize the scoring process according to specific requirements. For example, different scoring functions could be employed to optimize for different objectives, such as maximizing accuracy, minimizing cost, or balancing exploration and exploitation. Description of advantage 2. This component enables the RL chain to learn and adapt its decision-making process based on feedback provided by the selection scorer. By continually evaluating the outcomes of its actions, the RL chain can refine its decision-making strategy, improving its performance over time. This adaptation is crucial for the RL chain to become more efficient and effective in handling complex tasks and situations. For example, the RL chain could learn to select the best language model for a given task based on the scores assigned by the selection scorer. Description of challenges. Description of challenge 1. One challenge associated with the selection scorer is designing effective scoring functions that accurately reflect the desirability of different actions. These functions must be able to capture the complexity of the decision-making process and provide meaningful scores that guide the RL chain towards optimal actions. The effectiveness of the selection scorer is directly related to the quality of its scoring functions. So careful consideration and evaluation are essential. Description of challenge 2. Another challenge is finding the right balance between exploration, trying new actions, and exploitation, choosing actions that have performed well in the past. This balance is critical for the RL chain to learn efficiently and avoid getting stuck in local optima. The selection scorer can play a key role in balancing exploration and exploitation by incorporating mechanisms for exploring new actions and promoting exploitation of successful actions. For example, the selection scorer might use a probabilistic approach to select actions, sometimes choosing new actions and sometimes choosing actions that have performed well in the past. Langchainexperimental, RL chain, pick-best-chain, pick-best feature embedder. Definition. The pick-best feature embedder class is a component of LangChain's experimental reinforcement learning chain. It helps in selecting the optimal feature embedder for a given task from a set of candidates. This selection is based on the embedder's performance on a set of evaluation metrics. Components. Component 1. Pick Best Feature Embedder is a class responsible for selecting the best feature embedder from a pool of candidates based on performance evaluation. It is a crucial element in the LangChain experimental reinforcement learning chain, enabling efficient and effective task execution. Component 2. Evaluation metric is a critical component in the Pick Best Feature Embedder class. It quantifies the performance of each candidate feature embedder on a set of benchmark tasks. These metrics serve as the basis for selecting the optimal embedder for a specific task. Architecture. The Pick Best Feature Embedder class operates by first evaluating each candidate embedder on a set of benchmark tasks. This evaluation utilizes a specified evaluation metric, the embedder with the best performance, as measured by the chosen evaluation metric, is then selected as the optimal embedder for the given task. Role. The primary role of the Pick Best Feature Embedder class is to automate the process of selecting a best feature embedder for a specific task. This simplifies the workflow and streamlines the model training process. Advantages. Advantage 1. The pick-best feature embedder class significantly improves efficiency by automating the process of selecting the optimal embedder. This eliminates the need for manual selection and allows for quicker task execution. Advantage 2. By automating the selection process, the pick-best feature embedder reduces human intervention, leading to faster model training times. This is especially beneficial for tasks involving large datasets and complex models. Challenges. Challenge 1. Selecting the right benchmark tasks and evaluation metrics is crucial for ensuring that the chosen embedder is truly optimal for the target task. Careful consideration must be given to these factors to guarantee effective selection. Challenge 2. The evaluation process can be computationally expensive if the number of candidate embedders in evaluation tasks is large. It is essential to balance performance optimization with computational resources. For example, if we have a large number of candidate embedders and evaluation tasks, we may need to use a distributed computing framework or parallelize the evaluation process to reduce the computational cost. Langchainexperimental, LLMBashChain, auto-selection scorer. Definition. An object that automatically selects the best document from a list of candidate documents for a given query. This is achieved by ranking the candidate documents based on their relevance to the query. Components. Component 1. A list of candidate documents. This list of documents can be generated from various sources such as a database, a file system, or a web search engine. Component 2. A language model that scores each document based on its relevance to the query. This model is typically trained on a dataset of queries and relevant documents and can learn to identify the most relevant documents for a given query. Architecture. The auto-selection scorer is built on top of a language model that has been fine-tuned to perform document ranking. The model takes as input a query and a list of candidate documents, and outputs a score for each document. The document with the highest score is selected as the best document. This process of ranking the candidate documents is usually done by calculating a similarity score between the query and each document. This similarity score can be calculated using various techniques such as TF-IDF or word embeddings. Role. The auto-selection scorer plays the role of an automated document selector. It simplifies the process of identifying the most relevant document for a given query by automating the ranking and selection process. Advantages. Automates document selection, saving time and effort. For example, if you have a large collection of articles on a specific topic, the auto-selection scorer can quickly identify the most relevant article for a given query. Improves accuracy by leveraging a language model to score documents. This is in contrast to traditional methods for document ranking, which often rely on simple keyword matching techniques, which can be less accurate. Challenges. May require fine-tuning the language model for specific domains or tasks. This is because the language model needs to be trained on a dataset that is relevant to the specific domain or task. For example, if you want to use the auto-selection scorer to rank documents related to medical research, you will need to fine-tune the language model on a dataset of medical research articles. Can be computationally expensive, especially for large document sets. The process of ranking documents can be computationally intensive, especially if you are working with a large data set of documents. Langchainexperimental, LLMBashChain, VW Logger, VW Logger Summary. A descriptive overview of the VW Logger class, highlighting its components, architecture, purpose, benefits, and challenges. Components. Component 1. A class dedicated to recording interactions into a VW file. This class acts as a conduit for capturing and storing information related to the interactions between the reinforcement learning RL agent and the environment during training. It plays a vital role in building a comprehensive dataset that can be used for later analysis and model improvement. Component 2. This component is responsible for logging the training data used to train the RL agent, including the agent's actions, rewards, and state transitions, as well as evaluating the performance of the trained RL agent. It enables tracking and assessing the agent's progress during the learning process, allowing for insights into its performance and potential areas for optimization. VW Logger is built as a class specifically designed to work with VW Wabbit, a popular machine learning library renowned for its ability to handle massive datasets and intricate models efficiently. It allows for the seamless integration of the logging process into the training pipeline, providing a structured and organized way to store the data that powers the RL agent's learning process. The core purpose of the VW Logger class is to provide a robust mechanism for recording interactions with VW files. This logging capability is essential for training and evaluating reinforcement learning agents, as it allows for the collection and storage of critical data that is used for model improvement and performance assessment. VW Logger streamlines the process of training and evaluating reinforcement learning agents by offering a simple and efficient method for logging agent interactions. This functionality simplifies the development and deployment of RL applications, allowing researchers and developers to focus on building sophisticated agents without the burden of complex data management tasks. By integrating with the powerful VW library, VW Logger gains access to VW's advanced learning capabilities, such as its ability to handle massive datasets and complex models. This integration empowers VW Logger to handle the demands of sophisticated RL applications, ensuring that the logging process is robust and scalable. To ensure that the data logged by VW Logger is compatible with VW, it is crucial to format and structure the data correctly. This involves understanding VW's specific input requirements and ensuring that the logged information adheres to those specifications. Proper formatting guarantees that VW can process the data effectively, allowing for accurate analysis and model training. Logging large volumes of data can pose significant performance challenges, potentially slowing down the training process. It is crucial to optimize the logging process to minimize performance bottlenecks. This might involve exploring techniques such as asynchronous logging, batching data writes, and optimizing the size of logged data to ensure that the logging process does not become a bottleneck in the RL agent's learning pipeline. Langchainexperimental, RL chain, pick best chain, pick best event. Definition: a custom event designed for use within the pick best chain architecture. It signals that a specific chain has been selected from a pool of candidate chains. Components. Component 1. Chain ID, a unique identifier assigned to the selected chain, ensuring it can be distinguished from other chains within the system. For example, a chain performing sentiment analysis might be assigned an ID like sentiment chain 1. Component 2. Chain type specifies the type of the selected chain, providing a clear indication of its intended function. For example, the chain type might be question answering or summarization. Component 3. Chain score: a numerical score representing the selected chain's performance is determined by a evaluation function. This score allows the pick best chain to rank chains and choose the most suitable one for the given task. For instance, a chain might be assigned a score based on its accuracy in retrieving relevant information. Component 4. Chain output: the output generated by the chosen chain, representing the result of its processing. This could be a textual response to a query, a summary of a document, or any other relevant output. Architecture: this event is an integral part of the pick best chain architecture. This architecture works by evaluating a set of candidate chains against a defined task. Each chain's performance is assessed using an evaluation function, and the chain with the highest score is selected. The pick best event signals the completion of this chain selection process. Role: the pick best event acts as a signal indicating that a chain has been chosen and its output is ready for further processing. It effectively marks the end of the chain selection phase and allows the subsequent stages of a pipeline to utilize the chosen chain's output. Advantages: provides a structured way to capture information about the chosen chain and its output. It allows the system to record essential details about the selected chain, including its identifier, type, performance score, and output, ensuring comprehensive documentation of the chain selection process. Facilitates logging and analysis of the chain selection process. The event facilitates logging of all the chosen chains, scores, and outputs, enabling in-depth analysis of the selection process, identifying potential bottlenecks, and optimizing future chain selection strategies. Challenges: ensure the chain it is unique across different runs and environments. Ensuring that each chain identifier is unique across different runs and environments is crucial for unambiguous identification and tracking. This can be achieved through techniques like timestamping or using globally unique identifiers. GUIDs establish clear criteria for evaluating chain performance and assigning appropriate scores. Defining clear criteria for evaluating chain performance is essential to ensure that the evaluation process accurately reflects the desired outcomes. These criteria should be based on the specific task and the desired output characteristics. And the evaluation function should be designed to produce scores that reflect these criteria. Challenges: computational cost of embedding large amounts of text. Embedding large amounts of text can be computationally expensive, especially for large language models. This is due to the complexity of the models used to generate embeddings, which require significant processing power to handle the large datasets involved. For example, embedding a large corpus of documents might require a powerful GPU to process the data efficiently. Maintaining context for long texts. Maintaining context for long texts can be challenging for embedding models. When dealing with long texts, it's important to ensure that the embeddings capture the overall meaning and relationships between different parts of the text. This can be difficult for models that only consider local context within a limited window of words. For example, in a long article, embedding models might struggle to understand the relationships between different sections or paragraphs if they are limited to only considering a small number of words at a time. LangChain experimental RL chain base embed. Definition: the LangChain experimental RL chain base embed is a core element in the RL chain framework. It's essentially a blueprint for building and training intelligent agents that can respond to queries based on their understanding of the context. This blueprint includes three primary components: embedding function. This component is responsible for converting text into numerical representations. It's like turning words into a language that machines can understand. Reward function. This component assigns scores to responses based on how relevant they are to the original query. It's like giving the agent feedback on its performance, letting it know if it's doing well or not. Agent. This is the heart of the system. It's the intelligent agent that uses the embedding and reward functions to learn how to generate the best responses. Architecture. The RL chain architecture. Underpinning the LangChain experimental RL chain base embed is built on the principles of reinforcement learning. In simple terms, this means the agent learns by trial and error. It interacts with its environment, which can be a database of information or a collection of conversations. After every interaction, the agent receives a feedback signal called a reward. This reward tells the agent how well it's performing, encouraging it to repeat actions that lead to high rewards and avoid actions that lead to low rewards. Over time, the agent becomes better at generating responses that are relevant, informative, and accurate. Think of it as a student studying for an exam. The more practice the student gets, the more they learn and improve their performance. Role. The LangChain experimental RL chain base embed plays a crucial role in the RL chain framework. It's the building block for creating intelligent agents that can communicate and generate responses. This base embed serves as the foundation for building various agents capable of handling different types of tasks. Imagine you want to build a chatbot that can answer questions about a specific topic. You could use the LangChain experimental RL chain base embed to create an agent that is trained on a dataset of relevant information. Once trained, this agent would be able to understand your queries, retrieve the relevant information, and generate responses based on its knowledge. Advantages. The ability to learn from data and improve over time is a major advantage. This allows the agent to adapt to new information and become more sophisticated in its responses. For example, a chatbot trained on a dataset of customer service interactions can learn to answer commonly asked questions and provide helpful information, making the customer service experience more efficient and satisfying. The ability to handle complex and nuanced queries is another strength. The agent can understand the context of a query and provide relevant responses even when the query is phrased in a complex or ambiguous way. For example, if you ask a chatbot what are the best restaurants in New York City, it can understand that you are looking for recommendations for restaurants in a specific city and can provide a list of options based on your preferences. The ability to generate creative and informative responses is perhaps the most exciting benefit. The agent can use its knowledge and understanding to provide original and insightful responses, going beyond simply regurgitating information. This can be particularly useful for tasks like writing summaries or generating creative content. For example, a chatbot could be used to generate summaries of news articles or to create engaging stories. Challenges. Designing a reward function that accurately reflects the desired response quality is one of the key challenges. The reward function must be carefully designed to guide the agent towards generating high-quality responses. If the reward function is not designed well, the agent may learn to generate responses that are not actually helpful or relevant. For example, a reward function for a chatbot that simply rewards the length of the response might lead to the agent generating long, rambling responses that don't actually answer the question. Ensuring the agent learns effectively and avoids overfitting is another challenge. Overfitting occurs when the agent learns too well on the training data and is unable to generalize to new data. This can result in the agent generating responses that are only appropriate for the specific training data and not for the real-world scenarios. For example, an agent trained on a dataset of customer service interactions might learn to answer only specific questions that were included in the dataset and not be able to answer new questions that are similar but not identical to the training data. Handling situations where the embedding space is not representative of the desired response quality is a complex issue. The embedding space is a mathematical representation of the data that is used to train the agent. If the embedding space is not representative of the desired response quality, the agent may struggle to generate high-quality responses. For example, if the embedding space is based on a dataset of informal conversations, the agent might struggle to generate formal or professional responses. It's important to choose an embedding space that aligns with the desired output quality. Langchainexperimental, LLMBashChain, base embed. Definition. The base embed object acts as the fundamental building block for constructing reinforcement learning chains. It brings together the core elements essential for training an RL agent. These elements encompass reward function, a function that assesses the quality of an agent's responses. It guides the agent toward desirable behaviors by assigning rewards for actions that lead to successful outcomes and penalties for actions that do not. Agent, the heart of the RL chain. It interacts with the environment, learning from feedback to improve its decision-making abilities. This learning is driven by the reward function. As the agent seeks to maximize its rewards, environment defines the context within which the agent operates. This encompasses the rules of the game, the available actions, and the consequences of those actions. For example, in a game of chess, the environment defines the board, the pieces, and the legal moves. Observation, a snapshot of the current state of the environment. It provides the agent with the information it needs to make decisions. In a chess game, the observation would be the current board configuration. Action, the agent's chosen response to a given observation. It represents the agent's attempt to influence the environment based on the current state. Architecture. The base embed class forms the core of an RL chain. It coordinates the interplay between the agent, environment, reward function, and observation. The architecture is designed to enable iterative learning. The agent continuously learns and improves its decision-making capabilities through repeated interactions with the environment. It learns by trial and error, adapting its behavior based on the feedback it receives. Imagine a robot learning to walk. The robot repeatedly attempts to walk, adjusting its movements based on its successes and failures. Adaptive responses. The agent adapts its actions based on feedback from the environment and pay. Reward function. It can adjust its strategy based on new information and the rewards it receives. For example, in a game of checkers, the agent might learn to avoid certain moves that consistently lead to losses. Exploration and exploitation. The agent strikes a balance between exploring new actions and exploiting known successful strategies. Exploration allows the agent to discover new possibilities, while exploitation focuses on maximizing rewards from known actions. This balance is essential for optimal learning and performance. Consider a robot learning to navigate a maze. It might initially explore different paths, but once it finds a successful path, it will focus on using that path to reach the goal. Role. The base embed class serves as a fundamental building block for constructing reinforcement learning chains. It provides the framework and essential components for defining the RL problem by defining pay, environment, reward function, and agent. The base embed class formalizes the RL task. This includes specifying the rules of the game, the goals of the agent, and the actions available to the agent. For example, defining a self-driving car's RL problem would include specifying the roads, traffic laws, and the car's ability to accelerate, brake, and turn. Training an RL agent. The base embed class enables the agent to learn from experience, iteratively optimizing its performance. This learning process involves the agent taking actions, receiving rewards, and updating its strategies based on the feedback. An example of this is a chatbot learning to respond to user inquiries by interacting with humans, and adapting its responses based on the feedback it receives. Executing RL chains. The base embed class provides the necessary methods for running the RL chain, allowing the agent to interact with the environment and make decisions. It handles the flow of information between the components of the chain, enabling the agent to learn and act in the environment. Think of it as the conductor of an orchestra, ensuring that all the instruments play together harmoniously to create a successful performance. Advantages: provides a flexible and customizable framework for creating RL chains. It allows you to build RL chains that are tailored to your specific needs and goals. For instance, you can adapt the reward function, agent, and environment to fit your particular application. Simplifies the process of building and training RL agents. It provides a high-level abstraction that handles the complexity of RL, allowing you to focus on the specifics of your problem without needing to implement all the underlying components. This is like having a toolkit with all the tools you need to build a house, rather than having to manufacture each tool yourself. Encapsulates the core components of an RL system. This makes it easier to understand and reuse, and it helps ensure consistency across different RL chains. It's like having a blueprint for building a car, which outlines all the essential components and their relationships, allowing you to build different cars consistently based on the blueprint. Challenges: implementing effective reward functions can be challenging. Designing a reward function that accurately reflects the desired behavior and guides the agent towards optimal performance is crucial for successful RL. It requires careful consideration of the problem domain and the desired outcomes. Imagine designing a reward function for a robot learning to play soccer. You need to consider factors such as scoring goals, passing the ball, and defending against opponents. Balancing exploration and exploitation is crucial for optimal learning. Finding the right balance between exploring new actions and exploiting known successful strategies is essential for effective learning. Too much exploration can lead to slow progress, while too much exploitation can prevent the agent from discovering better strategies. This is like a chef who needs to try new recipes but also needs to use their proven recipes to satisfy customers. Langchainexperimental, RL chain, base, embed dict type. Definition. Components. Component 1. A dictionary that maps the name of the embedded document to the embedding itself. For instance, if you have a document named document1.txt and its embedding is a vector of 100 numbers, then the dictionary would have the entry document1.txt 1.23, 4.56, 99.01. This mapping allows easy access to the embedding of any document by its name. Component 2. This format is used by the embed retriever to store the embeddings of documents. The embed retriever is a component of LangChain used for retrieving documents based on their semantic similarity to a query. The embed retriever calculates the embeddings of documents and stores them in this dictionary format. When you search for a document, The embed retriever calculates the embedding of your query and compares it to the embeddings in a dictionary, returning the documents with the closest embeddings. Architecture. This variable represents the data structure used for storing and accessing embedded document. Representations. The embed dict type provides a simple and efficient way to organize the embeddings of documents in a dictionary format, allowing for fast access and retrieval based on document names. This structure is particularly useful for tasks involving semantic search and retrieval, where it is crucial to quickly retrieve relevant documents based on their meaning. Role. It facilitates the storage and retrieval of document embeddings, enabling efficient similarity search and retrieval based on semantic content. For example, imagine you have a collection of scientific articles and you want to find articles that are related to a particular topic. You could use the embed dict type to store the embeddings of all the articles. Then, when you search for articles related to your topic, you can calculate the embedding of your search query and compare it to the embeddings in a dictionary. The articles with the closest embeddings to your query would be returned as the most relevant. Results. Advantages. Provides a clear and structured way to store embedded documents. The embed dict type uses a simple dictionary format to organize the embeddings of documents, making it easy to understand and manage. Each document's embedding is stored with its corresponding name, ensuring a clear connection between the embedding and its source document. Allows for efficient lookup and retrieval of embeddings by document name. By storing embeddings in a dictionary keyed by document names, you can quickly access the embedding of any document directly using its name. This direct access is crucial for tasks like similarity search, where you need to retrieve the embeddings of multiple documents efficiently to compare them against a query embedding. Challenges. The embed dict type is not optimized for large-scale embedding storage, requiring alternative strategies for handling vast amounts of data. The embed dict type is a simple data structure suitable for small to medium-sized collections of documents. However, when dealing with very large sets of documents, storing all the embeddings in a single dictionary can become inefficient due to memory constraints. In such scenarios, alternative strategies like using databases, specialized data structures, or distributed storage systems become necessary to handle the large volume of data efficiently. Maintaining consistency between the embedded document names and the actual document content is crucial for accurate retrieval. To ensure accurate retrieval, it's essential to maintain consistency between the names used for storing embeddings in a dictionary and the actual document content. Any mismatch or inconsistency in these names can lead to incorrect retrieval, as the dictionary will associate an embedding with a different document than intended. This consistency is particularly critical when dealing with large collections of documents, as it prevents errors and ensures accurate document retrieval based on their content. LangChain experimental RL chain base event. Definition. A base event class for RL chain. Defining the structure of an event. It is a foundational component for understanding and tracking actions, observations, and rewards within a reinforcement learning RL context. This class provides a standardized way to represent events within the RL chain framework, offering consistency in data organization and analysis. Architecture. The base event class serves as a building block for constructing more sophisticated events, including those involving multiple agents or actions. This allows for flexibility in modeling complex scenarios within the RL chain system. It acts as a fundamental unit, enabling the representation of diverse event types within the RL framework. Role. This base event class provides a standardized structure for events within the LLMBashChain framework. It facilitates consistent data collection and analysis by ensuring that all events are represented in a uniform format. This uniformity allows for effective comparison, analysis, and interpretation of events across different RL experiments. Advantages. Facilitates data collection and analysis. By providing a consistent structure for events, it enables efficient and effective data gathering and analysis. Supporting the development and evaluation of RL algorithms, this standardized approach simplifies the process of extracting insights from event data, promoting better understanding of agent behavior and reinforcement learning dynamics. Supports diverse RL chain architectures. The base event class is designed to accommodate a variety of RL chain architectures, making it a versatile component for building complex and customized reinforcement learning systems. This adaptability allows for the construction of specialized event models tailored to specific RL applications. Challenges. Handling complex events involving multiple agents or actions. Managing events involving multiple agents or actions requires careful design and implementation to ensure accurate representation and analysis of the complex interactions within the RL environment. Addressing the intricate dependencies and coordinating data from multiple agents presents a significant challenge in maintaining a comprehensive understanding of the event. Ensuring compatibility with various RL environments. The base event class needs to be flexible enough to seamlessly integrate with different RL environments, ensuring that it accurately captures and represents the unique characteristics of each environment. Maintaining compatibility across a wide range of environments is crucial for the widespread adoption and application of the base event class in diverse RL projects. Langchainexperimental, RL chain, pick best chain, pick best selected. Definition. Detailed definition of the variable goes here. Components. Component 1. A chain that picks the best of a list of generated options. Using a reward function to determine the best, for example, in a text summarization application, the chain could be used to pick the best summary from a list of generated summaries, based on a reward function that measures the quality of the summary. Component 2. A reinforcement learning agent that learns to pick the best options, based on the reward function. The agent is trained on a set of examples, and it learns to pick the option that maximizes the reward. This can be used to improve the performance of the chain over time. Architecture. Description of the architecture supporting the variable. This chain uses a reinforcement learning agent to learn how to pick the best option from a list of generated options. The agent is trained on a set of examples, and it learns to pick the option that maximizes the reward. This architecture allows the chain to adapt to new situations and improve its performance over time. Role. Explanation of the variable's role in the system. This chain is used to select the best option from a list of generated options. This is useful when the generation process is not deterministic, and there is a need to select the best option from a set of possibilities. For example, in a chatbot application, the chain could be used to select the best response from a list of generated responses, based on the context of the conversation. Advantages. It can be used to select the best option from a list of generated options, even when the generation process is not deterministic. This is important in many applications, as it allows the chain to handle uncertainty and make informed decisions. It can be trained to pick the best option based on a specific Reward function. This allows the chain to be customized for different applications and to optimize for specific goals. Challenges. It can be difficult to train the agent to pick the best option. In all cases, this is because the agent needs to learn a complex mapping between the input options and the reward function. The agent may not be able to generalize to new cases if the training data is not diverse enough. This is because the agent may overfit to the training data and not be able to handle unseen situations. LangChain experimental, LLMBashChain, embed string type. Definition. This parameter specifies the type of embedding to use for input strings within the LangChain. Experimental, LLMBashChain, base module. The two allowed options are text and code, corresponding to embedding methods specifically designed for textual and code-based data, respectively. For instance, if you are using the module to analyze a piece of code, you would set this parameter to code, which would activate a code-focused embedding model. Components. Component 1. The embed string type parameter is a core component in the LangChain experimental, LLMBashChain, base module, defining how text inputs should be handled in LLMBashChain chains. It dictates the method used to transform input text or code into numerical vectors suitable for use in reinforcement learning algorithms. Component 2. It determines whether the embedding should be performed using a text-based or a code-based embedding model. This choice significantly influences the model's ability to understand and process the input, as different types of data require different embedding approaches. For example, a text-based embedding model might focus on relationships between words and phrases, while a code-based model would be more adept at recognizing patterns within programming syntax. Architecture. This parameter is a fundamental part of the architecture of LLMBashChain chains, which heavily rely on the representation of input data as numerical vectors. The choice of embed string type directly impacts the overall effectiveness of the chain, as it influences the model's ability to learn from and make decisions based on the input data. Imagine a chain designed to translate natural language code into executable code. The embed string type parameter would be set to code to ensure that the model appropriately captures the semantic structure and meaning of the code. Role. The embed string type parameter plays a critical role in the LangChain experimental, LLMBashChain, base module by controlling the type of embedding used for input strings. Its value determines whether the model will use a text-based or a code-based embedding approach, influencing the chain's performance and suitability for different tasks. For example, in a scenario where the chain is designed to answer questions based on a corpus of text, the embed string type parameter would be set to text to enable the model to effectively extract meaning from the textual input. Advantages. Advantage 1. Flexibility. This parameter enables the selection of the most appropriate embedding method based on the nature of the input strings, leading to more efficient and accurate results. It allows the user to tailor the chain to specific tasks by choosing between text-based and code-based embeddings. For example, when processing a dataset of code snippets, choosing code would provide better representation compared to text, leading to more accurate analysis and understanding of the code structure and functionality. Advantage 2. Improved accuracy. Using specialized embeddings for text or code can lead to more accurate results by providing a richer and more relevant representation of the input data. Textual embeddings focus on capturing semantic relationships between words and phrases, allowing the model to understand the meaning and context of the text. while code-based embeddings concentrate on the structural and syntactic aspects of programming. Languages, facilitating the analysis and interpretation of code. Challenges. Challenge 1. Choosing the right embedding. Selecting the correct embedding type for the input data is crucial for optimal performance. Mismatching the embed string type with the nature of the data can lead to suboptimal results, as the model might struggle to adequately capture the underlying meaning or structure of the input. For instance, using text to embed code snippets might not effectively represent the underlying code structure, leading to inaccurate analysis and interpretation. Challenge 2. Limited embedding options. The module currently supports only text and code embeddings, requiring further development for other data types. This limitation hinders the application of the module to a broader range of tasks involving diverse data types, such as images, audio, or complex data structures. Expanding the supported embedding types would make the module more versatile and applicable to a wider range of use cases. Description of the function. Challenges. Description of the challenge 1. While the string type instance function is effective for validating strings, it may not be suitable for all situations where type checking is required. In more complex scenarios, where custom data types or more intricate type hierarchies are involved, a more tailored type checking approach might be necessary. This is where the limitations of using simple is instance checks might become apparent. Langchainexperimental, RL-chain, base, embed dict type. Description of embed dict type. Components. Component 1. This attribute defines the type of dictionary that is used to store the embeddings for each document. For example, it could be a simple Python dictionary or a more specialized data structure like a Redis hash. Component 2. It dictates how the embeddings are organized and accessed within the system. For instance, it could specify whether embeddings are indexed by document IDs or by document content. Description of architecture. The embed dict type variable plays a crucial role in the organization and retrieval of document embeddings within the reinforcement learning chain (RL chain). This parameter governs the data structure used to store and access the embedding representations of documents, impacting the overall efficiency and effectiveness of embedding-based operations within the RL chain. Description of role. It determines the data structure and access mechanisms for embedding data, influencing the efficiency and effectiveness of embedding-based operations. By defining how embeddings are organized and accessed, this parameter significantly impacts the performance of embedding-related tasks, such as similarity search, document retrieval, and question answering. Description of advantages. Allows for flexible and efficient storage of embeddings, enabling optimized retrieval and processing. This flexibility ensures that the system can adapt to different embedding formats and access patterns, leading to improved performance in retrieving and processing embeddings. For example, using a specialized embedding database like FICE can enable efficient similarity search over large collections of embeddings, supports diverse embedding formats and facilitates integration with different embedding models. This versatility allows the system to work with a wide range of embedding models, including those generated by different application programming interfaces, APIs, or libraries. This enables the system to leverage the latest advancements in embedding technology without being restricted to a single format or model. Description of challenges. Choosing the right embed dict type requires careful consideration of the specific requirements and characteristics of the data and task. This decision involves balancing factors such as storage efficiency, retrieval speed, and the specific needs of the embedding-based operations. For example, if the task involves performing similarity search over a large dataset, an efficient embedding search index like FIS or ANOI would be preferred. Maintaining consistency and compatibility between embedding storage and retrieval operations is essential for accurate and reliable results. This requires careful management of the embedding data structure and ensuring that all embedding operations are performed using the same data format and indexing scheme. Inconsistent handling of embeddings can lead to errors in retrieval, similarity comparisons, and other embedding-based operations. LangchainExperimental, LLchain.base.is string type instance. Definition. This function determines whether the input is a string-like type. For example, if the input is hello world, the function will return true. However, if the input is 123, the function will return false. Components. Component 1. LangchainExperimental, LLchain.base.is string type instance. Architecture. This function uses the built-in Python function as instance to determine if the input is a string-like type. The function will return true if the input is a string, a Unicode string, or a bytes object. Otherwise, it will return false. For example, if the input is hello world, the function will return true. However, if the input is 123, the function will return false. Role. This function is used for type checking. For example, a function might use this function to check if the input is a string before processing it. In addition, this function can be used to help ensure that functions receive the correct type of data. Advantages. This function is used to check the data type. It helps ensure that functions receive the correct type of data. For example, a function might use this function to check if the input is a string before processing it. In this way, it can help prevent errors by ensuring that data is of the correct type. This is helpful when writing software that works with user input, as user input can be of various data types. Challenges. This function may need to be extended to handle additional types of data. For example, if this function is to be used with a language model, it would need to be extended to handle the model's output. Furthermore, if the function is to be used with a specific domain, it might need to be modified to handle the types of data used in that domain. LangchainExperimental LLchain base embed dict type. Definition. Components. Component 1. A dictionary that maps the document to its embedding. For example, in a document retrieval system, the document could be a news article and the embedding could be a numerical representation of the article's content, which can be used for similarity search. Component 2. A dictionary that maps the document to its text. For example, the document could be a customer service chat transcript and the text could be the entire transcript content. Architecture. The architecture supports the variable by providing a structured way to store the embeddings and text associated with documents. The variable facilitates efficient retrieval of documents based on their content, which is crucial for tasks like question answering, document summarization, and information retrieval. Role. The variable plays a crucial role in storing and retrieving information related to documents, enabling efficient processing and analysis. It provides a central repository for document representations, allowing various components within the reinforcement learning chain to access and utilize the information efficiently. Advantages. Efficient storage and retrieval of document embeddings and text. The variable enables quick access to document representations, improving the performance of applications like question answering and document summarization. facilitates seamless integration with other components within the RL chain. By providing a consistent structure for storing and retrieving document information, the variable promotes interoperability between different components in the reinforcement learning chain. Challenges: maintaining consistency between the embedding and text representations. Ensuring that the embedding accurately captures the meaning of the document's text is a critical challenge. The quality of the embedding can significantly impact the performance of downstream applications. Handling large volumes of documents and embeddings efficiently. Managing large amounts of data can be computationally expensive and require efficient indexing and storage techniques. The scalability of the variable is crucial for real-world applications that involve massive datasets.